Assalamu alaikum. Hello, everyone. My name is Khalid Jamiel. I'm a third year medical student. And today we're going to be doing the second part of the BEP crash course, which is going to be covering all your post-midterm BEP lectures, inshallah. So before we start, the post-midterm lectures are easier, generally speaking, but they're a lot more in content. So this video might take a bit longer than the part one video. However, it's easy, inshallah. So we're going to be covering confidence interval. Then we're going to cover hypothesis testing, then correlation analysis, comparison of means, ANOVA, and finally principles of epidemiology, which are 3 lectures, but I put them as one. So let's start with confidence intervals. Now, this lecture ties in very much with the pre-midterm content. So if you don't remember the pre-midterm content at all, please have a look at the slides at least to just refresh your memory. Okay, so what are confidence intervals? We use confidence intervals when we want to estimate population mean from a sample set data set. So whenever we have a sample and we get their data, we cannot generalize to the population unless we have a confidence interval. So we usually use a 95% confidence interval, and this is its calculation. Okay, but we'll talk about the calculation later. Let us understand how we interpret the 95 confidence interval. So the interpretation of 95% confidence interval is we are 95% confident that the population mean lies in this range. So because we're generalizing the data from the sample to the population, we can't just say, oh yeah, for sure, that's the case. We say we're 95% confident that the population mean lies in this range, which is an interval. An interval means basically from 1 to 5. This is an interval, okay? And we'll understand a bit more when we look at the examples. Okay, another interpretation of the confidence interval is that 95% of repeated tests or parameters would fall in this range, okay? And another interpretation of confidence interval is the 95% confidence interval will contain the population mean 95% of the time. Why am I saying the same thing again in 3 different ways? Because these are the ways they ask about it in the final exam, and you need to memorize it word for word like your name, because this is exactly how it's going to come in the exam. And the other 4 options are going to look very similar to these. They're not going to be very different. So you need to memorize those word for word. The first one is we are 95% confident that the population mean lies in this range. The second one is we are 95% of repeated tests or parameters would fall in this range. And this is the most commonly asked one in the past. And then there's the 95% confidence interval will contain the population mean 95% of the time. The most confusing option with it is that there is a 95% chance of a parameter to fall in this range. Now, why is this wrong? Because the parameter either falls or does not fall in this range. So it's either 0 or 100%. You can't say there's a 95% probability or chance. As soon as you see the word chance or probability in an option for the interpretation of confidence interval, you need to remove that option automatically, because it's not talking about probability. If it's not talking about chance, it's saying that we're 95% confident that the population mean, the actual population mean that we don't know, is going to fall in this confidence interval we gave. And we're also saying that if we do other tests for other samples, 95% of them are going to fall in this confidence interval. So for example, let's say the mean of a sample A was 8, okay? And our 95% confidence interval was 6 to 10, let's say, okay? So this is the 95% confidence interval, and obviously the mean is in the middle. So we're saying that if we were to do sample B and sample C and sample D and sample E, let's say, 95% of those will fall in the range of 6 to 10. The means of 95% of those will fall in the range of 6 to 10. We're also saying that if we were somehow able to find the actual population mean, we're 95% confident that it will fall in this range. This is not the same as there's a 95% chance of a parameter to fall in this range, okay? So please be very careful. This is very important. I think there's a mistake in the past where the answer is there's a 95% chance, and that's wrong. That's the wrong answer. Okay, so Let's practice. So it says calculate the 95% confidence interval with a sample of 36, sample mean of 120, and standard deviation of 12. So let's look at the equation of the confidence interval. So it's the mean plus minus 1.96 times SEM. Okay, where do we get 1.96 from? Just to refresh our memory. So basically, this is a normal distribution. Okay, and this is the mean. Okay, the 95% confidence interval is basically when we have 2.5 outside here and 2.5 outside here, and then in the middle we have 95%. Okay, so this is basically what 95% confidence interval is. So we need to find these values. This is basically what we're finding. So where did 1.96 come from? If you go back to the Z table, we'll find, you guys go back to the Z table, we'll find that 1.96 corresponds to 2.5%, okay? And that's why we use 1.96. Okay. And then, so for the 95% confidence interval, we need to get this Z value and this Z value. And then we need to convert it to the actual numbers. And then that's how we get the confidence interval. But this is a very simplified equation, okay? So you don't need to really know anything I said. You just need to memorize this equation, but just to understand what 95% confidence interval is and where it came from. So let's do it over here. We have a sample of 36. So n equals 36. And then we have a mean of 120 and a standard deviation of 12, okay? So sigma equals 12. Now SEM, if we recall from pre-midterm, it's standard deviation over the square root of n, which is 6, okay, square root of 36, which is 6. So that's 2. So SEM equals 2. And then we use this equation. So the mean, which is 120, so 120 plus and minus 1.96 times 2, okay? And so that will be, let me calculate it just 1 second. 1.96 times 2, so 3.92. So 120 plus 3.92 and 120 minus 3.92. So 123.92 and 120 minus 3.92, that's 116. 116.08. So this is the confidence interval between 116.08 and 123.92. This is the confidence interval, and this is how we calculate it, okay? We're gonna practice more examples later on, but this is how we use the equation. Okay, now this is another type of question they can ask. They said find the SEM from this confidence interval, which is 4.55 to 19.45, where the mean is 12, okay? So now we have the mean, so 12 plus minus 1.96 x, because we need to find SEM now, equals, equals what? So if it's plus, then it will equal 19.45. And if we use minus, it will equal 4.55. I hope you understand this point, because in the normal equation, we add and subtract, okay? If we subtract, we'll get this one. If we add, we'll get this one, okay? So that's basically what we're doing. So let's try this. So so now we get 1.96 x equals 4.55 minus 12, so 7.45. And then x equals 7.45 over 9.6. 7.45 divided by 1.96, which will equal 3.8, okay? So the SEM was 3.8. Let's try with the plus just to make sure of our answer. 12 plus 1.96x will equal 19.45. صح ده المفروض. Whatever, okay? So now we take 12 to the other side. So 19.45 minus 12 equals 7.45. And then again, 1.96 over 7.45 will give, 7.45 over 1.96 will give us our answer. Okay? طيب, now let's answer this. Please answer this question before I say the answer. Repeated sampling of a population is done with 95% confidence interval. which of the following would be present 95% of the time? So answer yourself. So the mean of the population, because we said here, we're saying that parameters 95% of the time will fall in this range, okay? Which of the following statements about a 95% confidence interval is correct? Answer this again by yourself. His answer here is C, because we said chance, we delete it out all, and then we are talking about the population mean, so it's parameter, it's always parameter, okay? Okay, so now let's talk about the relationship between confidence interval and sample size, okay? So again, the same concept as standard distribution and the same concept as SEM. As you increase sample size, you decrease the width of the confidence interval, okay? So what does that mean? So we have something called precision of the confidence interval. It's measured by the width of the confidence interval, okay? The narrower, the more precise. The wider, the less precise, okay? This is very important, very, very important. The narrower the confidence interval, so let's say the mean is 12, then we have a confidence interval of 10 to 14, and then we have another confidence interval of another sample of 12 people, but their confidence interval is in another sample with a mean of 12, but their confidence interval is, let's say, 8 and 16, okay? So this one is more precise, okay? This one is less precise because it's wider, okay? Now, when we increase the sample size, the confidence interval is narrower and the precision increases. So if we take the sample size of this sample, it will probably be 50. And if we take this one, it will probably be 30, okay? So that's why it's less precise. So 30 people, their mean is 12, but their confidence interval is wide. 50 people, their mean is 12, but their confidence interval is narrow and more precise, okay? So as you increase sample size, you're making the confidence interval narrower and more precise, okay? Now, when we, let's say we took sample A, okay, and their mean was 8, and their confidence interval was 6 to 10, okay? So this is the confidence interval, 6 to 10. Now, sample B, another sample, a total different sample, their mean will be something different, okay? And their confidence interval will also be either narrower or wider. So let's say, depending on the sample size. So let's say in this example, 4 to 12, okay? So both the position of the curve, so the position of the normal distribution would change in different samples, okay? And so this is sample A and this is sample B. And the width of the confidence interval will also change, okay? You don't need to understand anything. This, you just need to memorize. When we take different samples, this is exactly how they'll ask you. If we take two different samples, what will be different about their distribution and the position? I mean, the width of the distribution and the position, you say it changes, both change in case we take different samples. If we increase sample size, if you use the same sample, so sample A, for example, has 10 people, and we just add more participants, we make them 20, the position will not change, the location will not change, but the width will change because now it will become more precise or narrower, okay? So this is very, very important. Sometimes they ask you what happens if we take two different samples. If you take two different samples, the location is going to be different and the width is going to be different. If we take the same sample, we just increase the sample size of that sample, then the width is going to change, not the location. This is exactly how they're going to ask about it. So just memorize it this way, okay? Now, confidence interval and statistical significance. Now, this, I'll just introduce something. I'll touch way more upon it later on. I'll just introduce it now. Whenever we're doing a statistical test, we have two hypotheses. We have the null hypothesis and we have the alternative hypothesis. So let's say, for example, we're testing if smoking increases the risk of lung cancer, for example, okay? So we take a sample of smokers and a sample of non-smokers, and then we compare the amount of people who have lung cancer in both groups, okay? So if we find a true difference between them, we say that smoking does increase lung cancer. If we don't find a true difference between them, we say that smoking does not or is not related to lung cancer, okay? So the hypothesis that smoking is not related to lung cancer is called null hypothesis, okay? This is the null hypothesis. And no, whatever we're testing is not true. There's no true difference, okay? If we find a difference, we say this is the alternative hypothesis, okay? So this is the basic concept. Now, how can we use the p-value early on? And we said that if the p-value is less than 0.05, we say that data is significant, okay? And that means the null hypothesis is wrong and the alternative hypothesis is true, okay? We can also use confidence interval in order to see if the data is significant or not. We have something called the null value, okay? And the cutoff, as we said, is, let's say for p is 0.05, because we have a null value for the means itself, okay? If it crosses that null value, if it's more, yani, then we say that the null hypothesis is false. And if it doesn't, then we say that the null hypothesis is true. And we'll see that in a graph in a bit, okay? Now, we also have something called effect size. So now we have, is the data statistically significant or not based on statistics? But there's also clinical significance, okay? So let's say, I'll give an example and then explain what these mean, okay? So let's say you gave group A placebo. Placebo means no drug, okay? And you gave group B a drug, okay? And both are obese, they're obese, okay? And you want to see if drug C, for example, has an effect on reducing obesity or not, okay? So this is what you're trying to test, okay? So let's say we did the p-value and we look at the confidence interval and it was statistically significant, okay? Can we على طول say, oh, drug C is good for obesity? No, we can't say that because maybe it is statistically significant, but it only decreases the weight by like 2 kilograms or 4 kilograms, okay? So there is a difference between the two groups, the people who took the drug and the people who didn't take the drug. There is a difference, but it's very minimal. So we say it's statistically significant. It can be statistically significant, but it's not clinically significant. Right? So if it's statistically significant, but not clinically significant, so what do I want with the drug? I'll say يعني مفروض. There's no need for this drug, صح? So, and how do we measure the clinical significance? We have something called the effect size. Okay, and we're going to touch upon the effect size multiple times during the course of the 6 lectures. It's a very important concept. And this is the difference in means between the sample and population. Okay? So, as we said here, we want to see how different the means actually are, okay? And the effect size is usually obtained before a study. So for example, I want to make a study for, again, this drug, okay? And I say, if this drug doesn't decrease the weight by at least 10 kilograms, I don't want it, even if it's statistically significant, okay? So we put the clinically significant point at 10 kilograms. If it's more than 10 kilograms, then it's both statistically and clinically significant. If it's not more than 10 kilograms, then it's not, okay? I know I'm saying it all in words now, but it will make much more sense when we go to the graph, okay? So why do we use both p-value and confidence interval? There are a few problems with p-value. The first problem is that we can make a decision on whether or not to reject the null hypothesis. So we can make a decision on whether or not it's statistically significant or not. But the first mistake is that it's subject to error, okay? So we may be accepting the null hypothesis when it's false, okay? So for example, we can say that, oh, this drug does not have an effect, but in reality, it does have an effect, okay? So the p-value alone is subject to error. And that's why we need confidence interval to see if that error is made and to help to see if the statistic is clinically significant. This is what we've been explaining so far. Confidence interval also kind of shows the effect size as well. So it shows whether it's statistically and clinically significant or not. P-value only shows if it's statistically significant. It doesn't show if it's clinically significant. Okay. So that's why we use confidence interval and p-value. You can't use one without the other. Now this diagram hopefully is gonna make everything I said very, very much clearer. So in scenario A, the null, as we can see, we said this is the null value. Okay, I was talking about earlier. We said if the confidence interval touches the null value, then we accept the null hypothesis and we say there is no statistically significant difference. Okay. If it doesn't touch, like over here, it doesn't touch, then we say it's statistically significant because it's not null. It's not touching the null value, okay? So we have multiple cases, okay? The first case is that the confidence interval, this is the confidence interval. This is where it starts, this is where it ends. It's not touching the null value, as you can see, okay? And it's over the important value. The important value is the effect size we put from the beginning. We say that the drug is important, clinically important, if it does more than 10 kilograms difference, for example, okay? So it's not touching either. So it's more than the null and it's above the important value. So in this case, we definitely reject the null hypothesis, okay? We definitely say that this drug is clinically important because it's both statistically significant and clinically significant. This is definitely a good study and it's definitely a correct مو definitely يعني بس very likely to be a correct result, and so we reject the null hypothesis على طول without thinking. In scenario C, I'm going to skip B because it's not important. In scenario C, we can see that it doesn't touch the null value, so it's statistically significant, but it does not cross over the important value. Okay, so it's not clinically important. Okay, so it's statistically significant, but it's not clinically important. So in that case, we repeat the test with different or more samples to see if we just made an error and that's why it's statistically significant but not clinically significant, or we want to see if it's actually not clinically important. So we repeat it just to be sure. Okay, so this is scenario C. In scenario D, we can see that the confidence interval is so wide, and that means it's very unprecise. We said wider is less precise. So this is very, very low precision. This is very wide confidence interval. And because it's very low precision, it touches both the null value and it also crosses above the important value. So this is probably a very bad study, okay? And this shouldn't be the case. And in this case, we definitely repeat with different and more samples. And we say that this sample has low power. This test has low power, or this study has low power. And we'll understand what power is in the next lecture, okay? But this is a question guaranteed 100%. They'll ask you if the confidence interval touches the null value, so it's not statistically significant, and also crosses above the important value. So what's wrong with this test? You say that what is true about this test? You say that this test has very low power, okay? And you need to repeat with different samples. Very important test. And in scenario E, it's touching the null value and it's also not crossing above the importance. So this is definitely wrong, and we accept the null hypothesis out. We say there's no difference. There's no statistically significant difference, and there's no clinically significant difference. And we can see that the confidence interval is actually narrow, so it's probably a precise test. So خلاص, there's no we accept the null hypothesis. We say that, for example, smoking has no relation with lung cancer, or the drug B does not cause a decrease in weight, okay? So this is basically it. It's a very important slide. If they ask you anything, it will be definitely about scenario D. So be very, understand scenario D well, okay? The rest aren't that important, but scenario D is very important. And note that this is all at a 5% significant level. I don't want you to understand this, just memorize it, that whenever we're using the confidence interval, whenever we're rejecting the null hypothesis, we say that we reject the null hypothesis at a 5% significant level. If we accept the null hypothesis, like in this case, we say that we're accepting the null hypothesis at a 5% significant level. And you guys might be confused about null and not null. There's a whole lecture about it. It's going to be very much clear later on. But I guess you have the basic idea to understand what I'm talking about at least. Okay, so now again to the problems with the p-value. We said the first problem with the p-value is that it shows us if the data is statistically significant, but it doesn't show us if the data is clinically significant or not. Okay, so that's the problem with the p-value. So, and it's also subject to error. Okay, so we have two cases, very important. It always comes in the past. If we have a small p-value means less than 5%. Okay, so less than 5% equals statistically significant. But we have a small effect size. Okay, so the effect size is very small. So there's no difference between the two means we compared. So if there's no difference between the two means we compared, there's no big difference. At least there is a difference, and it is statistically significant, but it's not clinically significant. So it may be statistically significant but not clinically significant. This is the problem with it. Okay, memorize this line very well. If we have a significant or a small p-value with a small effect size, so small plus small, then the data might be statistically significant because the p-value is small, but it's not clinically significant because the effect size is small as well. Okay, if we have an insignificant or large p-value, okay, and then we have a large effect size, okay, so this is just like this case, like case D, okay, then it may be clinically significant even though it's not statistically significant. Okay, so we need to repeat the tests again because it definitely crossed over the important value or the effect size we want, but it's not statistically significant. So how does that make sense? So we need to repeat it with more sample size or another sample. The last two examples are the normal examples or the good examples. So if you have a significant p-value and a large effect size, we say all good. Then we definitely reject the null hypothesis. We reject null. Okay. If we have an insignificant p-value but a small effect size, then we definitely accept null and we say there is no difference. Okay. So now let's practice. Which of the following increases the width of the 95% confidence interval? Answer alone. And then, so the answer is, we said increases the width. Okay, increase width equals less precision, and less precision comes with a small sample size. So the answer is C. What does 9% confidence interval mean? Again, so the answer here is C. Okay, so we reject the null hypothesis outside this interval at a 5% confidence interval. So if the interval does not contain the null value, does not contain null, then we reject the null hypothesis, just like this case over here. Okay, it does not contain null, it does not contain null, it does not contain null. So we reject the null hypothesis at a 5% significant level. Okay, so this is how the questions might come. What happens to the 95% confidence interval if you increase sample size? Again, we said increase sample size equals more precision, which equals less width. But what happens to the location? No change to the location. So the answer is A. The problem with a study that obtains a small p-value and a small effect size may be that, answer this one alone. Okay, so the answer here is, we said small p-value, so significant, statistically significant, but not clinically significant. It's maybe not clinically significant. So the problem is an unimportant effect is reported as statistically significant. This is the answer. Okay, so it's not an important effect, but it's reported as statistically significant. Okay, an easy way to do this, not confuse yourself, small p-value, على طول take out not statistically significant because it's definitely statistically significant. And then you can choose from the other two. And obviously, because there's a problem, then an unimportant effect is reported as statistically significant. This is not a problem. So you can guess by logic sense, okay? Or common sense. So that's it for the first lecture, which is confidence interval. If you're confused, don't stop and go back and try to read the lecture. Finish this lecture, hypothesis testing, because it's going to make it much easier, null and alternative, rejecting and accepting. So finish this lecture and then study both together. I'll also recommend that as soon as you finish a lecture, go and solve the blue file, the classified past papers, in order to stick the information in your brain. I know if you leave all the solving until the end, you're not going to actually retain anything. So solve as soon as you finish a lecture. Okay? Like hypothesis testing. So what is the whole idea of research? Okay, we want to test hypotheses. Okay, and we said we have two types of hypotheses. We have null hypothesis and we have the alternative hypothesis. Okay, so null hypothesis means there is we didn't find a significant difference or a significant effect. An alternative hypothesis means we did find. Okay, so let's give an example. Let's say I'm a cardiologist and I suspect that a certain protein M is elevated in myocardial infarctions. You remember the lecture about biomarkers of myocardial infarction? Okay, so I suspect that a certain protein M is elevated in myocardial infarction. So I take a sample of a normal population and a sample of an MI patients, and I measure the mean level of this protein M. Okay, so the mean protein levels of the normal sample was 1, and the mean of the MI sample was 10. Okay, so now what do I do with this information? I want to see if this difference, so is there a difference between 1 and 10? Definitely. But was this difference caused by chance, by error in the HADA, or is there an actual difference in the M protein levels? Okay, so this is what I'm testing. Okay, so this is the question: is there a real difference between the population, between the two populations or the two samples, or was it caused by chance? Okay, so this question is answered by hypothesis testing. Okay, so this is the basic theme of the lecture. Now there are two possibilities. Number one, there is no real difference in the protein levels, and the difference is caused by chance. So there's no real difference in the population. So MI people do not have elevated M protein compared to normal people, but we got a different value because by chance. Because we're taking samples, we're not taking the population. Remember, okay? And in this case, this protein cannot be used as a marker for MI. And this is called null hypothesis. Okay, so now we're accepting the null hypothesis. We're saying that the null hypothesis is true. What is the null hypothesis? Is that there is no real difference in the protein levels, and the difference is caused by chance. Okay. The second possibility is that there is a real difference in protein levels, and this protein can be used as a marker for MI, and this is called the alternative hypothesis. Null hypothesis, from now on, I'm going to refer to it as H0 in the slides, and alternative hypothesis, I'm going to refer to it as H1. Okay, so H0 is null, H1 is alternative. Okay, and in case of treatment, for example, if we're trying two different treatments, or let's say we're using, we want to see if a treatment has an effect in a certain population, let's say obese patients again. So the alternative hypothesis can also mean that this drug has a positive or a negative effect. And it has an effect. Okay, so this is a question commonly asked in past papers. It says, what is the alternative hypothesis if we're trying drug A on two populations? The alternative hypothesis is that this treatment has either a positive or a negative effect. It has an effect. Okay, so it doesn't have to be a positive effect. It doesn't have to be a beneficial treatment. It may be a bad treatment, and we reported, we said that this treatment بالعكس made it worse. So this is a significant result. Okay, so this is also part of the alternative hypothesis. Okay, so don't confuse yourself in the exam. Don't rush and answer the drug has a positive effect and not read the rest of the options and put this as an answer. لا. It's drug has positive or negative. So I hope this slide is clear, and this is going to be the main theme of the lecture. Okay. Now, how do we interpret the statistical significance? Again, we're back to the p-value, but now we're going to be talking about the p-value in very much detail. So what is p-value? Okay, so p-value is a probability, okay? And you remember the probability lectures when we said P/A/B, stuff like that. So this is also applied to p-value, okay? So the p-value is the chance of the result happening, assuming that the null hypothesis is true. Okay, so this is what the p-value is. So this translates to, we calculate the p-value assuming that the null hypothesis is true. 100% a question about this. We're going to tell you what assumption do you make when calculating the p-value? Or how do we calculate the p-value? We calculate it assuming that the null hypothesis is true. This is very important, okay? So if the probability that we get the result when the null hypothesis is true is 5%, okay, or less than 5%, that means that it is probably false, and therefore we see the data is significant, okay? So again, let me explain this in other words. If the probability that the null hypothesis is true, because now we're assuming that the null hypothesis is true, okay? If we assuming that the null hypothesis is true and the probability of that happening, which is the null hypothesis is true, is less than 5%, then the null hypothesis is probably false, okay? And we accept the alternative hypothesis. And that's why we say when the p-value is less than 5%, then we reject the null hypothesis, okay? So p-value of less than 0.05 or 5%, we reject the null hypothesis because we assumed it's true, but we got a probability of 5%. So that's a very, very, very low chance. So we say that's probably false, and that's why we reject it. We reject the null hypothesis when p-value is less than 5%. Okay? You don't need to understand this in depth at all. If you didn't understand fully, just memorize that we calculate the p-value assuming the null hypothesis is true. خلاص, just memorize this, and that's enough for solving questions. If the p-value is less than 5%, we reject the null hypothesis, and we say this piece of data is statistically significant, and we did not get the difference in the means by chance. We did not get it by chance. We got it because there's a true difference between the two populations, okay? I hope that makes sense. So when we say the data is statistically significant, we are saying that we are going to reject the null hypothesis and accept the alternative hypothesis, okay? Now, there are four possibilities when we accept or reject the null hypothesis. We can reject the null hypothesis and it's false, okay? And that's perfect, صح? We're basically here accepting the alternative hypothesis. Now, from now on, guys, I'm not gonna use from both perspectives. I'm only gonna talk from the perspective of the null hypothesis. When I say reject null hypothesis, that's by automatically accepting the alternative hypothesis, okay? So if I say we for example, reject this, we reject that there is no real difference in the protein levels, then I'm accepting this على طول, صح? So statisticians like to talk in terms of null hypothesis. I don't know why they flipped it. It's way easier to understand it as accepting the alternative hypothesis. But anyways, when we reject the null hypothesis, when it's false, that's okay, that's good. When it's actually false in the population. We can accept the null hypothesis when it's true, and that's also good, okay? So we did the correct option. So for example, because we took a sample, okay, of MI patients and non-MI patients, okay? And we saw a difference, and we calculated the difference using the p-value, and we said, wallah, the p-value showed that there's an actual difference between the two populations. Now we're saying that all the MI patients will have the elevated M protein, and all the normal patients will not have elevated M protein in the population, in the actual people, not the sample, okay? And that's rejecting the null hypothesis. If we accept the null hypothesis, we're saying that this difference we found here is not true to the population. It's not true. We found it by chance, by errors, okay? So I hope you understood this concept. It's very important. Now, there are two errors, okay? So these two are correct decisions. And no, wallah, we rejected the null hypothesis when it's actually false in the population, or we accepted the null hypothesis when it's actually true in the population. Obviously, there's no way we can know if we did the correct choice or not. They're all percentages, wallah. There's a 95% chance, for example, that I did the correct option, okay? So we can't know for sure, because the only way to know for sure is getting the actual population mean, which is impossible. You can't get all the MI patients in the world and calculate their M protein levels, okay? So now the two errors are rejecting the null hypothesis when it's true, okay? So that's the first error. We rejected the null hypothesis and it's true. So we said that there is a true difference in the population between MI patients and non-MI patients, but in reality, there is no true difference, okay? So that's an error, and that's called type 1 error or alpha error, okay? Very important, guys, to understand this, okay? To memorize this, actually. And then the second error is that we accept the null hypothesis when it's false, okay? So we said that there is no difference, but in reality, there is a difference, okay? And now we're saying there is no difference, okay? So these are the two types of errors. Now, the first thing we said, the first possibility, which is rejecting the null hypothesis when it's false, which is basically accepting the alternative hypothesis. This is called the power of the study. Okay. And this is what we were talking about earlier. Okay. Now, when we say a study has high power, that means there's a high probability that we are doing this possibility. Okay. So we're always aiming for high power. If a study has lower than 80% power, the result isn't that reliable. Okay. And unfortunately, that's most of the studies, they have a power less than 50%. But so if the study has high percentage power, so there's a high percent chance that we got the right option and that we rejected the null hypothesis and we reject the null hypothesis when it's false. Okay. If you have low power, then we might fall in this error, type 2 error, which is accepting the null hypothesis when it's false. Okay. So I wanna wait, let me show you something. Okay, so this table is a very nice summary. Okay, so in this over here in the top, we have the reality. Okay, so this is the actual population. Okay, and here we have our sample or the experiment. Okay, H1 equals alternative hypothesis, H0 is non-hypothesis. So the first HADA is accepting. So this is accepting, this is rejecting. So we're accepting the alternative hypothesis in the sample, and it's actually true, okay, in the population. So this is power, okay? If we are rejecting the alternative hypothesis when it's actually true in the population, then this is beta error, okay? So beta and power are opposite of each other. Now, in the other side, we have alpha, which is rejecting the alternative hypothesis, Wait, no, alpha. I'm sorry, guys. Alpha is rejecting the null hypothesis when it's true, which is accepting the alternative hypothesis when it's false. Okay, so we're accepting the alternative hypothesis in our sample when it's actually false in the population. This is a false positive, basically. The beta error is a false negative. Okay, so it's not negative, but we interpret it as negative. In this case, it's not positive, but we interpret it as positive effect. Okay, so you get it. Now, a way I like to remember it is art bath. This is a mnemonic my friend gave to me 5 minutes before the exam. And honestly, I forgot everything I just told you guys. So I panicked in the exam. Then I remembered this mnemonic and it saved me all throughout the exam. So just remember it. Alpha is rejecting the null hypothesis when it's true. I'm always talking in terms of null hypothesis. Okay. Beta is accepting the null hypothesis when it's false. Okay, so whenever you encounter the question that tells you what does alpha mean, what does beta mean, use this mnemonic. It's very good. Art, bath. Okay. So that's it for this slide. I hope you understood it. Okay, so now let's talk in more detail about power. Okay, so we said power is the probability of rejecting the null hypothesis when it's actually false. Okay, so which is accepting the alternative hypothesis. Okay, so we have things that increase statistical power, and these are things we want. Okay, they're good things for us. Okay, so the first thing is a larger difference between the means. Okay, and here I'm talking about the means of the population. Okay, so if we have an actual larger difference between the means, then the power of the study increases, okay? And this is interpreted as an increase in effect size, okay? So how do we calculate effect size? We take the mean of one population and then subtract the mean of the other population from it and then divide it by standard deviation. This is effect size, okay? So you might be asked to calculate the effect size. We're comparing, for example, let's say as population A has a mean of 125, population B has a mean of 120, and their standard deviation is 5. So the effect size equals 1, okay? Now, the higher the effect size, the more the difference between the two populations, and obviously the stronger the power. So when you increase effect size, when you have higher effect size, you are increasing the power. Now, this is something we can't control. We can't control if there's an actual big difference between the two populations. That's what we're trying to test aslan. So we can't control this, but it's good for us. It will increase the power, but we can't control it, okay? The other thing that we can control is the sample size. Okay, so if we increase the sample size, you're increasing the power of the study. Okay, so increasing sample size basically makes everything better. Okay, it makes the confidence interval more precise. It makes the distribution narrower. It does many things, and also it increases the statistical power of the study. Very important. Every single exam comes. Okay, and decreasing variability in the sample. Okay, so let's say I have sample A, and sample A, for example, I take a random sample. Okay, if مثلا sample A were mostly females randomly, okay, and they're all, let's say, in the same age range, okay, that means between within the sample we have few little variance, okay, little variability in the in the sample, and that will increase our power. Okay, if we have in the same sample, wallah, someone that's 90 years old, white, and then a black 20-year-old female or مدري ايش, so that's very, very much variability within the sample, and that will decrease the power. But again, we can't always control the variability within a sample because we have to pick randomly. Okay, so the thing we can control to increase the statistical power is sample size. Now, this is an important point, yani, because they might get you what can we change to increase power, and they might get you this in the wallah larger effect size or larger difference between the means, but you can't change that. So what you have to choose is increase sample size. Okay, now these aren't very important. I just put them there for completion's sake. You can read them in your own time, but they're not important at all. Okay, these three are very important. Now, statistical decision making. Okay, so alpha, the probability of alpha is preset by the study design. What do I mean by that? So let's say I have a study and we said alpha is the probability of rejecting the null hypothesis when it's actually true. Okay, so it's saying that this drug has a difference when this drug does not have a difference in reality. Okay, so that's alpha. Now we set this at the beginning of the study. We say that for this study to be valid, I want alpha, the chance of alpha happening to be less than 5%. Okay, and you're you kind of get where I'm getting to here. 5% again. Okay, so this is exactly the same as p-value. Okay, and this is a new concept. To determine significance, we are basically comparing the p-value with the alpha error we put in the beginning. Okay, we set the alpha error to be 5%. So we're saying that if the probability of alpha error happening is less than 5% in this study, then this is probably statistically significant. Okay, and the difference between p-value and alpha is alpha we set from the beginning, we say 5%. Okay, but p-value we calculate. So p-value might be more than 5%, p-value might be less than 5%, but the percentage of alpha error happening we set from the beginning of the design. Okay, and we say that if the p-value is more than this, is more than 5%, then this stat is not statistically significant. If it's less than 5%, then it's statistically significant. You don't need to understand all of this. Just memorize one line from here. Is that to determine significance, we are basically comparing p-value to the alpha error, okay, that we set at the beginning of the design. Okay, so this is the only thing you need to know. Don't overthink it. If you didn't understand anything from what I said, that's okay. Just memorize this line. Okay, just try to grasp just enough to be able to solve the exam questions. Don't try to overthink or deep it. Yani, this is not our work. This is the statistician's work. We just need to know how to interpret. Okay, so now what happens if, let's say, we set the alpha error at 1% in the beginning? So we do a lot of things. The first thing is that we decrease the probability of alpha happening. Okay, so that makes sense. Okay, so we decrease alpha, so we're decreasing the probability of alpha. Okay, we're increasing the probability of beta error. Okay, so if we're decreasing the probability of one error happening, we're increasing the probability of the other error to happen. Okay, so that's why we set it at 5%. We think that's a reasonable number. If we make it at 1%, okay, we'll be saying that the p-value has to be less than 1% in order for the data to be significant. And if we're saying that, then we are also increasing the chance of accepting the null hypothesis, because now, even if the p-value was 4%, I will accept the null hypothesis. Earlier, if the alpha is 5, okay, and we got a p-value of 4, then we will reject the null hypothesis. But if the p-value of the alpha now is 1%, and I'm comparing the p-value to 1%, that means if the same 4% that I got in the other design, on the other study, I got it here, it will be insignificant reported, and it will we will accept the null hypothesis. And that's an error because it might be true, okay? So I might accept the null hypothesis when the null hypothesis is false, okay? So yeah, this is why I have. And then we also decrease the power of the study. Now, this is a very important formula, okay? Power is 1 minus B, okay? Because here, if you can see, it's either power or beta, right? If we, for example, if we accept the alternative hypothesis, which is if we reject the null hypothesis, okay, let's put it in this way. If we reject the null, we are either power or beta, right? Because alpha is accepting the null. Now we're rejecting the null. So if we reject the null, we're either power of beta or beta. So if the probability of power happening is 80, then beta will be the rest, okay? If the probability of beta is 80, then alpha will be, the power will be the rest, okay? So that's why power is 1 minus beta, okay? And also beta is 1 minus power, okay? So if in this case we decrease alpha, we said if we decrease alpha, we will increase beta. So if this is more, this is going to be less, صح? They're opposite, okay? So if we increase this, okay, then power is going to be less, okay? So very important. So now we linked power to sample size, and we also linked it to the alpha, okay? Very important. Okay, so that's it for this lecture. Let's move on to correlation analysis, which is the easiest lecture out of all of them, okay? So I'm gonna give you, I'm gonna explain without the text and then go read the text quickly, صراحة, because it's very easy, okay? So what is correlation analysis? Correlation analysis is we're trying to see literally if there's a relationship between two variables, okay? So let's say I'm comparing between weight and height, okay? So height and weight, let's say, okay? So we put height in the x-axis and we put weight in the y-axis, okay? And so people who, let's say, have a higher weight will have, higher height will have a higher weight. People who have a less height will have a lower weight. That's normally the case, صح? And so in this case, we say that these two variables are correlated and they're associated, okay? And it will probably look something like this, okay? So we say they have a linear positive relationship. As height increases, you're also increasing weight, okay? So this is a relationship, a positive relationship. And when one is increasing, the other is also increasing. Okay, so let's apply this to the actual stuff. For example, let's say we want to compare between, let's say, smoking and lung cancer, for example. Okay, so we put smoking here. It doesn't matter what we put in the X and what we put in the Y, and lung. Okay, and it's going to look something like this. Okay, if we plot all the points, it's going to look something like this. And this is called a scatter plot, okay? Because in real life, you'll never have a straight line, okay, or straight dots, okay? You'll have a scatter plot like this. So if you can see that most of the hada, so if we draw a line of best fit in the middle, we'll go like this تقريبا, okay? So we do say they have a linear positive relationship, again, because increased smoking, pack per year, for example, pack per year of smoking will increase the lung cancer, okay? Let's say exercise and obesity, okay? Exercise and obesity. Okay? Now, in this case, بالعكس, people who exercise more will have less obesity or less weight, okay? Let's say weight, okay? Weight. Okay? So it will actually go something like this when we draw all the plots. It will go something like this, okay? So yeah, you get the point. So we're trying to see if there's a positive or a negative relationship, okay? So that's the basic concept of correlation analysis. Now, let's read the text. correlation analysis is used to examine the strength of association between continuous variables. Okay, this is a key word, continuous. So it has to be number. No, sorry. It has to be numbers. Okay, so if you remember what continuous variables is, height, weight, age, stuff like that. So numbers. Okay, what if we have variables that are not continuous? We don't use correlation analysis to see the association. We use chi-squared. Okay, and chi-squared they didn't talk about in detail in this course. The only thing you need to know about chi-squared is it's used to determine the association between categorical variables, which are either ordinal or nominal. So nominal or ordinal variables, we use chi-squared. Continuous, we use correlation analysis. This is very important, very high yield, and there's definitely going to be a question about this, okay? So they won't ask you straight out, oh, what test of correlation, what test of correlation will we use for categorical? La. They'll give you a case. They'll tell you we're trying to compare, for example, blood groups, the blood group with the chance of lung cancer, for example. So that's categorical because blood groups is nominal. Okay, so you can't use correlation analysis. You'll use chi-square. If it says we're trying to see the hada between the test scores and let's say height, for example, whatever. Okay, or caffeine intake or whatever. Okay, so numbers. So that in that case, you'll pick correlation analysis. Okay, so be smart about picking. Now, we said a linear relationship shows the association between two variables as a straight line. It can be expressed as y mx plus c. C is the y-intercept. M is the slope of the hada, but this doesn't really matter. Scatter plots, okay, this is important, shows the association between two continuous variables. Just like we explained, smoke pack per year with the prevalence of lung cancer, for example. Okay, so this is shown by scatter plots. Okay, this is important. Correlation coefficient. Okay, so what is correlation coefficient? It basically describes the strength and this is strength, by the way, it's not strength and the direction of the relationship between two variables. So let's say we have two variables, x and y. We have other two variables, a and b. A and b, okay? So this shows a scatter plot like this. Very scattered, okay? This one shows a scatter plot like this. Okay? So which one do you think is more correlated? There's a stronger association between which two variables? It's definitely x and y, okay? And is it a positive correlation or a negative correlation? Both are positive, okay? So both are positive. So what's the difference between their associations? This one is stronger. This one is weaker because they're more spread out, okay? And this is what the correlation coefficient basically tells us. So it tells us the direction and the strength, okay? So we have two types of correlation coefficients. We have the parametric type and we have the non-parametric type. Very high yield. This is the most important thing in the lecture, okay? So the parametric coefficient correlation coefficient test is called Pearson's test, okay? Or R, the R value, okay? The non-parametric is called Spearman's test or RS, okay? So the RS value, okay? Now Spearman's is not important. It's not important calculation, but it's very important. It's always asked about because what's the difference between the parametric and non-parametric test? In the parametric correlation coefficient, we do it based on assumptions about the distribution in the population. Okay, so we assume that the population is normally distributed. Normal distribution, okay, is only established if we have a continuous variable. Okay. Okay, we can't make a normal distribution of a non-continuous variable, okay, like a nominal or ordinal, okay? In the case that we have ordinal or nominal, we cannot use Pearson. We use Spearman or non-parametric test, okay? على طول, okay? And these do not rely on assumptions of the population. We use it for non-normally distributed data, like categorical data which are basically nominal or ordinal data. Okay, very important differences. Yani 100% a question on the exam. When do we use parametric? When do we use non-parametric? So parametric assumes a normal distribution. Okay, non-parametric does not assume normal distribution. Parametric is continuous data. Non-parametric is categorical data. Very important. Okay. And it can also be used when we use ranked data instead of using the actual. For example, let's say we're comparing age with height, okay? Or age with IQ, for example. Let's make it more realistic, okay? And both of those are continuous, okay? But for example, the data set came out as 50, 70, 79, whatever, and the IQ came out as 200, 150, whatever, okay? So these are all continuous, okay? But sometimes we wanna rank those data, okay? Okay, let's add one more piece of that. Okay, let's add one more piece of data. Let's say let's make this 74 actually, okay, and let's make this 14. Let's make this 80, whatever, okay, and then we make this 14, for example, okay? So sometimes we want to rank the data instead of using the actual data. So let's say we rank this as 1, the top, the most IQ, and we rank this as 2. We rank this as 3. We rank this as 4, okay? Why do we do that? Because this is obviously an outlier, okay? So it's way off, and we know it's an outlier. And so if we want to eliminate the effect of outliers, we can rank them, okay? 1, 2, 3, 4 is much closer than 200, 150, 134, and 14, okay? So sometimes we do that. So these are continuous, okay? But we ranked them. As soon as we ranked them, we made them ordinal, okay? They're no longer continuous, okay? So in that case, we also use Spearman, okay? So I hope the slide is clear. Very easy, صراحة. Okay. One point is that Pearson is R for the sample, but it's this sign, I don't know what it's called, صراحة, for the population. So remember when we said there's a parameter and statistic, this one is the statistic, which we are always going to use, and this one is for the population. They never asked about this. I don't think they'll ask, but I put it for completion's sake. Okay, so let's talk more about the Pearson's correlation coefficient, or R, okay? So first thing, it has no units. It's just a coefficient, okay? A ratio, basically. And secondly, it's always between or equal to -1 and 1, okay? So it's either -1 or 1 or something in between, okay? So we said that we determine the strength and the direction of the relationship between the association. And how do we do that? So the sign, so positive or negative, determines the direction of the correlation. So obviously negative correlation means when one increases, the other decreases. Positive correlation means when one increases, the other increases, and vice versa, which means when one decreases, the other also decreases, okay? The magnitude is determined, or the strength is determined by the number itself, okay? So the sign determines the direction, whether it's negative, positive. The magnitude of the number determines how strong the relationship is. So the magnitude of 1, whether it was positive or negative, means perfect correlation. Means when this one increases by 1 unit, that one increases by 5 units. This one increases by 2 units, that one increases by 10 units, okay? So it's perfect correlation. And 0 means absolutely no relationship, okay? Totally off. So it will look something like this on the scatter plot. Okay, no relation whatsoever, okay? So, and this applies for both the negative and the positive sides, by the way. Okay, so this is very important. 0.8 to 1 is strong correlation. 0.4 to 0.7 is moderate correlation. 0.1 to 0.3 is weak correlation. And we need to put these numbers and the signs together. So this is how they'll ask in the exam. The R value was found to be negative 0.5. So in that case, we say it's a moderate negative correlation, okay? Now, this is the equation for calculating R, okay? Very, very long, very complicated. صراحة, I prepared the answer key here because they'll ask you how to calculate it. So, but I'll explain it for completion's sake, okay? So this is the equation. We need the x values and we need the y values, obviously. We need the mean of x and the mean of y, and then we'll do these calculations, okay? So the first thing is these are the x plots and these are the y plots, okay? So then the first calculation is x minus x and y minus the mean of y. So x minus the mean of x is all of this, y minus the mean of y is all of this, okay? But then we need to multiply them by each other, okay? So when we multiply this by this, obviously we got the mean, okay? When we multiply all of this by this, so minus 2 minus 2 is 12, minus 1 minus 3 is 3, 0, 0, 0, 1, 3, 3, 2, 6, 12. So the total, so over here, the total is 30, okay? So that's the first part of the equation. Now let's look at the denominator. We need this squared, okay? So we got all of this squared, and then the total of this squared minus the total of this squared, okay? So 10 minus 90, basically. And so we put it all above each other. So r equals 30 over the square root of 10 times 90. And we get a correlation of 1, which is perfect correlation. Perfect positive correlation. Okay. So I don't think they're going to ask you about the صراحة مستحيل. Now, Pearson's correlation has some limitations, okay? The first very important slide. The first thing is that sometimes two variables are related but non-linear relationships. So they might be related like this. So Pearson correlation only sees if there's a linear relationship. What if the relationship between two variables was up and then down? And this is very common in clinical practice. يعني a drug مثلا reaches an optimal point and then it drops, for example, or protein reaches up هذا optimal and then drops. So this cannot be tested by R, okay? So if there's equal between the right and the left, the R will show as 0. I will show you that there's no correlation. And in fact, there is a correlation, and it increases and then decreases, okay? So that's the first disadvantage. The second disadvantage is that outliers greatly affect R. Remember we said if we have outliers, we need to rank, and then we use Spearmans. But what if we don't rank them and we use Pearson's anyway, and there's an outlier? It will affect R very much, but it will not affect Spearman because we already ordered the data and we made it order, okay? So I explained this point already. I hope it makes sense. The third disadvantage is that we cannot extrapolate R beyond observed ranges. So let's say we observed the change, the difference in IQ between the age range of 50 to 80, for example, and we found a positive R of, let's say, 0.7. So what is this? This is a moderate positive association between age. It's probably going to be negative. Okay, so a negative moderate association between age and IQ. So as you increase in age, you decrease IQ. Can we say that this is the case for all ages? لا. We say between the age of 50 and 80. We cannot say for 40, the age of 40 or the age of kids, for example. لا. We need to specify the age range we tested. We cannot extrapolate the data outside that range. We cannot use the same finding outside the range of data we try to test, okay? This is another disadvantage. The last disadvantage is that we cannot establish causation. So for example, again, the example of age and IQ. We said as you increase age, you decrease IQ. Is age what's causing the decrease in IQ? Is it? We don't know. You can't say that. Even if they're associated, association, and this is a very important concept, okay? Association does not mean causation. It does not mean causation. It does not mean that one caused the other. It just means that they're associated. But that's the only thing you use. But then you do further tests to see if they're causing each other or not. But with the R value alone, you cannot tell, okay? So memorize this slide very well. They might ask you any one of the 4 of these, but in the past, they only asked about these 3 so far. But they might ask you about this, okay? So memorize all of them. Okay, so we're done with this lecture. Let's talk about comparison of the means. Okay, so in this lecture, the main theme is that you remember hypothesis testing when we're seeing if the p-value is significant or not and stuff like that. what tests do we use in order to compare the means أصلا? Okay, so when we're trying to test the hypothesis, the null hypothesis is that there is no difference between the two means that we're testing. Okay, so the mean of the obese patient that took the drug and the mean of the obese patient that didn't take the drug, there is no significant difference, and so that's the null hypothesis. Okay, so how do we compare these two means? With what test exactly? And this is what we're going to talk about in this lecture. Okay, so you remember the z-test. Z-test was one way to compare between the two means. The whole calculations we did, and then we looked at the z-table, we took out the p-value, and then that's how we compared the mean. Okay, but now we have something called the t-test. This is more realistic. You remember I kept on telling you guys that you cannot, you rarely know the actual mean of the population and the actual standard deviation of the population. You can rarely know that. No, you can't go around Riyadh asking everyone in Riyadh about their weight, for example. So you don't know the mean and the standard deviation of the population normally. They give it to you in questions, but in real life, you rarely know that. Okay, so in reality, we don't use z-test because we can't use z-test because we don't know the actual standard deviation. We use something called t-test instead. Okay, so when the population standard deviation is known, we can use z-test. That's rarely the case. However, we rarely know the standard deviation, and therefore we estimate it from our sample. Okay, in that case, we must use t-test, and this is more 100%, million% a question in your exam. They'll ask you, when do we use t-test? When do we use t-test? We use t-test when we don't know the standard deviation and we estimate it from our sample. Okay, and we use z-test when we know the standard deviation. Another place where we can use z-test is if the sample is more than 100 people. Okay, if the sample is more than 100 people, then we can use the z-test and the t-test, because if we get a clinical trial, for example, and we get more than 100 participants, that's probably a very strong study, and the standard deviation of that study will probably be very similar to the actual standard deviation of the population if done properly, and that's why we can use the z-test as well as the t-test. But that's rarely the case. We rarely use a sample more than 100, okay? And so that's why we mostly use t-test. But why do we rarely use a large sample size? You remember when we kept saying that a large sample size, the more precise confidence interval, it's a narrower distribution, a lot of benefits of getting a more sample size, statistically speaking. But practically speaking, a very large sample size is not a good thing. First of all, it may be difficult to get this many sample size, okay? May be difficult to get 100 patients with a certain disease. May be difficult to get more than 100 patients who are even willing to participate in the study. And so it's not practical. A very high sample size is not practical. It's very good statistically. It will be very accurate, but it's not practical in real life. The second thing is that obtaining a small sample is cheaper and faster. And we're all under budget, and we don't have unlimited budget to do research. And so we usually use smaller sample sizes. We don't use very small sample sizes, but we don't use very big sample sizes either. We use a small sample size, okay? And the third thing is that me as a human, I get tired, صح? If I have a large sample size, I have so many things to test for, okay? And so many people to test. And so that will I'll probably put less focus on each patient in the sample, okay? And that will lead me to probably make errors, and it will make the data in the end less accurate, okay? Now, this does not have to do with it statistically being less accurate. لا. If we do everything perfectly, then statistically, more sample is more accurate. But as humans, we are probably going to make more mistakes if we have a higher sample size, and we're not going to focus on each patient as much as we will do if we have a small sample size. So we have three benefits of small sample size. One, it's difficult to get a high sample size. Two, it's very expensive, and it will take a lot of time. Three, when we have a large sample size, it may not be good because in the end, the interpretation of the results will be the obtaining and the interpretation of the results will be probably less accurate if you have a high sample size. just focus on this and obtaining the result. Us, when we obtain the results and when we test the result, there's a higher chance of error and a higher chance of less accuracy if we have a large sample size. So this is 100% again question in the exam. And why do we use a small sample size? And these are the reasons. And so when we use a small sample size, we always use t-test, okay? And this number is important, more than 100. If more than 100, we can use the z-test. They may ask you about that as well. Okay, so t-test. Again, this table يعني مشوار صراحة. But don't remember them asking us to use the t-table. I don't know if it's required or not, but it's in the slide, so I put it for completion's sake. But there are some important stuff, okay? So we calculate and use t-test exactly the same way we calculate and use the z-test, okay? So review that before coming here because I'm not gonna repeat everything again, okay? I'm gonna explain assuming that you understand everything about how to use the z-test, okay? So this is the t-table, and you'll notice that it's a different format, okay? So in the t-table, this is the t-table. The one we used to use is the z-table. The t-table, the left column, this one over here, shows something called the degree of freedom. What is the degree of freedom? It is the sample size minus 1. Okay, this is the degree of freedom. And they might ask you, okay, I'll explain this later, okay? Just keep it in mind for now that this is called degree of freedom, and this is the sample size minus 1. The top row over here gives the right tail probability, okay? So you remember in the Z table, the p-value was in the middle, and the p-value showed the right tail probability. In the T table, the column over here shows the right tail probability. Okay, so what's the probability of it being more than this T? So this is basically P. Okay, so this part is P. And in the middle is the T value, but the T values we can get. But in the middle, we call it the minimum T values. Minimum T values. They're not actual T values, they're minimum T values. And why do I focus on this point? I'll show you in a minute, okay? So the steps again is calculate the t-value, which is sample mean minus population mean over SEM. Obviously, we use SEM لأنه it's sample. We never use t-test when we know the actual population. Find the closest t-value that is less than the value you found, okay? So if you find 10, obviously this is not a realistic t-value. If you find 10, as a t-value, you might not find 10 in the table, but you might find 9, and 9 is the closest one to 10, so you pick 9, okay? So that's why I say minimum t-value, okay? You can't pick anything less than 10, obviously. You can't pick the second less thing than 10. You have to pick 9, and you don't pick the closest thing to 10 and wallah above 10. You can't pick, for example, 10.1. You have to pick the thing less than 10, okay? So the minimum t-value. Okay, so find the closest t-value that is less than the value you found and see what the right tail probability it corresponds to. Okay, so then if you find this, you'll go up here, you find the 0.01. And then you multiply that p-value by 2. Again, the same thing, because you don't only want the right side, you want also the left side. And this is significant, this is also significant. And whatever in the middle is not significant. Okay, whatever. Okay, so again, just memorize multiplying the p-value by 2, just like we did with the z table. Okay, so it's the same steps, but the interpretation of the table is a bit different. Okay, so let's practice. So a sample of 12 obese patients, n equals 12, received a blood glucose test. The mean upper range of the normal population is 100. We want to test if the mean blood sugar of obese individuals is higher than the upper limit. So is it actually higher than 100 or not? The mean was 109.8 of the obese patients. So X is 109.8. And what is it? This sample size is 12. Okay. With a standard deviation of 11.6. So SD equals 11.6. Okay. And so to calculate, the first step is calculate the t-value. Okay. So we calculate the t-value by sample mean minus population mean. So the population mean is 100. So mu is 100. So 109.8 minus 100 over SEM. So what is SEM? SEM equals standard deviation 11.6 over the root of 12. Oof. So SEM equals, let me calculate that. 11 divided root of 12. Divided square root of 12. Okay. 11 divided the answer. صراحة I'm on my phone calculator, so it's not, I don't know how to calculate it. الزبد. When you get SEM, okay, and I remember the value was 11, and you'll get 2.9 something. I remember, okay, you get 2.9 something, and the closest value to 2.9 something is 2.7. The 2.7, this one, okay, whatever it is, okay. So this was the closest value I remember, okay. Not this one. It was corresponding. This was this one. Sorry, it was this one. Okay, and this corresponds to 0.01. So the right tail is 0.01. Now we want the left tail as well, and so we multiply by 2, and so it's 0.02. Okay, so the p-value in the end is 0.02. Okay, now is this statistically significant? Yes, it's less than 5%. Okay, so this is how we use the t-test. Okay, and so we say that yes, there is a significant difference, and the mean glucose levels of obese patients is higher than the upper limit of the normal population with a p-value of 0.02. Okay, so this is how we use the t-test. Now, this is how they write the result. This part, صراحة, is not important only for your exam, but it's important also for later on when you're doing research, if you want to participate in a journal club or something. This is how they report the data. And so they say T11, 11 is the degree of freedom. Okay, so we said the degree of freedom is 11. Okay, p-value of 0.02, effect size of 0.84, and a 95% confidence interval between 102 and 117. I recommend you guys practice how to calculate the confidence interval again. The mean was 109.8, and the SEM was whatever you calculated. Okay, and try to get these values. That means you understood the confidence interval equation well. Okay, and so this is how they're going to record the data, and then they're going to put a figure next to it with the confidence intervals. Okay, so 117 is here, and 102 is here, and this is the mean. And this is the null value, which is 100. Okay, is it touching the null value? No, it's not touching the null value. So the confidence interval graph is also showing statistical significance. Okay, so this is how you read it. Now they might give you exactly this, and they tell you what was the sample size. How do we get the sample size from this? Degrees of freedom. We said degree of freedom equals sample size minus 1. Okay, and the sample size was 12, if you remember. Okay, so even if they don't give us this whole case, we know that the sample size is 12. Okay, so very important. They definitely ask you to get the sample size from this. Okay, and you need to know that degree of freedom equals sample size minus 1, and you need to know how to interpret this. You need to know how to interpret this, everything. Okay, another example. So T22. So what's the sample size? 23. Is this statistically significant? لا, because this is 25%, not statistically significant, and effect size also is very low, much lower than this, if we can see. Okay, so effect size here is big, which means there's a big difference between the but here the effect size is very small. And so this is the normal population, placebo. This is the people who take caffeine, for example. And the 95% confidence interval was minus 4.25 and 15.3. So they're overlapping. So this is the mean of the normal population. It crosses it. It crosses the null value. And so even the graph shows, and no, this data is not statistically significant. Very, very important, guys. So overlapping confidence intervals of the control group and the treatment group means that the treatment didn't actually do a statistically significant difference. We can see that they're close together. They're overlapping. If this was above, not touching, then this would be statistically significant. But because the confidence intervals are overlapping, we say no, wallah, the effect size is not that big, maybe. Okay, but it's if one is here and the other one is here, then that's definitely statistically and clinically significant. Okay. Now we have different types of t-cells. This is also very, very important. This whole lecture is very important, Salah, and it's asked about a lot. Okay, so we have two types of t-tests. We have paired t-tests and we have independent t-tests. The differences between these two tests and when we use each is very, very important. Okay, so other names for paired t-test is paired, related, correlated, or dependent samples. All of them mean the same thing. Okay, paired, related, correlated, dependent. You need to know all of those names because they might ask you any of these names, okay? But the most common one is paired, okay? Because they can ask related, they can ask correlated, they can ask dependent, okay? Now, there are three examples when you have paired, related, correlated, or dependent samples, okay? This simply means that you are testing the same group, okay? The same people. Yani you obtain one sample and you do the test of this sample only. You're not comparing two groups together. You're comparing one group and two different treatments. And so we have three cases where we can call it paired or related or correlated or dependent. The first one is that when you test the same group before and after the treatment. So you have only group A, you don't give them treatment, you test their blood for, let's say, a certain protein level, okay? And then you give them the treatment, and then you see if this protein level elevated or not, and you compare the old with the new, okay, in the same individual. So that's a paired t-test or a dependent t-test or a correlated t-test. All of them mean the same thing, okay? The second example is when you test two different treatments in the same group, okay? So group A, same group A, in the beginning we give them a treatment B, and then when the effects of treatment B go away, obviously you measure whatever you want to measure during this period of treatment B. Then you wait for a bit for the effects of treatment B to go, and then you give them treatment C in the same individuals, okay? And then you see the effects of treatment C. Okay, so that's another example. A third type, which is a special type of paired test, is more matched pairs. Okay, this is a special type in which now we have A and B. But A and B have to be basically the same in terms of characteristics. You get identical twins, for example, in group A and group B. They have the same genetics, they have the same characteristics. So خلاص, it's basically as if you're using the same people. Okay, this is basically the idea behind it. Obviously, it's not the same as using the same sample, but it's still considered a paired test, and it's a special type called matched pair. Okay, and it doesn't have to be identical twins. It can be, مثلا, we are matching them according to common characteristics. مثلا, all young white females, both groups. They're young white females that look like a similar height, similar weight. Okay, so that's another way we can do it. And then we give those two the same treatment, and then we see, or we can give this group treatment A, this group treatment B, and then we compare. Okay. So this is paired. Okay. So the data is usually correlated. There's usually a correlation between the two pieces of data. Okay. So if we tested the drug and then another drug, there's usually a correlation. We don't need to understand what that means in detail, but just know it because they might ask an MCQ about this. But this is from the name, it's a correlated sample. Okay, so there is correlation in the paired t-test, and the sample sizes in the two groups are always equal. Even if we use two different groups, we have to use 12 and 12, for example, okay, or 13 and 13. And obviously, if you're using one group of people, then definitely the sample size in both tests are going to be the same. So this is an important point. Independent samples is exactly the opposite. We're using completely different groups, giving one treatment and the other the placebo. So we take a random group of people and call them group A, and another completely unrelated, independent people, and we call them group B. We give these people the placebo, and we gave these people the normal, the treatment, and then we see if there's a difference between them. So this is simply an independent t-test. And the sample size can be equal, It can be equal. If you choose to put 12 and 12, okay, but doesn't have to. So in many studies, you'll find that the placebo group is 40 and the treatment group is 54, and that's valid. Okay, so we can do that in independent, but it's not possible logically to do that in the paired test. Okay, even if you use the matched pair, it has to be equal samples. So and this is usually double blind. Okay, so this is basically an RCT in which neither the guy who gives the treatment or the uh the person knows if they're getting the placebo or not. Okay, and this is important to reduce bias. Okay, so مثلا if I'm in a control randomized control trial in which we're testing if a drug treats, for example, Alzheimer's. Okay, and if I know that this patient is placebo and me, the person who was administering the drug, if I know this person is placebo and this person is not placebo, and I like the person that's getting placebo more, I'll switch them out. I'll give the placebo person a drug, and that guy, the other guy that I don't like, I'll give the placebo. And thinking that I'll benefit the guy I like. And that's bias. Okay, so that's why neither I nor the patient should know if they're getting placebo or treatment, okay, to eliminate bias. Now, we do some assumptions for all t-tests, whether it was independent or paired or whatever. If it was, we assume that the sample is random, okay, so we randomly pick people. We didn't pick people according to who we like, who we didn't like. We didn't pick people in wallah, all females or all males, okay, so we're picking a random sample. And we are assuming that the participants are independent of each other. So what happens to a participant does not affect the other participant, okay? And the third assumption we're making is that population data is normally distributed, okay? And we only do this for small groups, which is less than 15, okay? If it's more than 15, then probably the population is normally distributed, but for very small sample size, we also assume that the data is normally distributed. So memorize these one. They're just gonna ask you, wallah, what is an assumption of a t-test, and you need to pick one of these three. So I hope this slide is clear. We're almost done with this lecture. So what are the advantages and disadvantages of paired and independent t-test? When do we use this? When do we use this? So the advantages of the paired t-test is that it avoids problem with variability. So when we're taking an independent sample and we're doing an independent t-test, because we randomly pick the people in group A and group B and they are totally different, the variability within the group is going to make a problem. لأنه if we have young people here that are healthy and we have young people here that are not healthy, for example, that's a variability, and that might be a confounding factor. Confounding means a variable other than the variable we're testing. So, for example, we're testing the efficacy of the drug. When a variable other than the drug may improve or make the condition worse, that's a confounding bias. That's something else that's affecting the trial, and that is due to variability between the patients. So if we're using the exact same patients, then there's no variability between the two different groups. Yani the person A here is the same as person B, basically, because we're giving the treatment to the same people. Okay, so theoretically we're eliminating confounding or variability between the two hada. Except in matched pairs, obviously there's going to be a little bit of variability, but there's still way less than independent. Okay, so it avoids problem with variability between the participants, and this increases the power of the test. Very, very important. And this is the most important thing in this slide. And paired tests have higher power than independent tests because there's less variability, and that's why there's a way less chance to make type B error, which is accepting the null hypothesis when in true it's false. Okay, because we might accept the null hypothesis because of the variability between the patients, not because the drug, not because of Madrid. And when you use the paired t-test, that's very unlikely to happen. So we're increasing the power of the test. So that's all you need to know from this center, okay? And also we need fewer participants, obviously, because we're using the same 10 people in group A, we're using them again, okay, in the second test. But in independent, we need to get 10 people in A and 10 people in B as well. Okay, so we need 20 people total. The disadvantages is that order effects, very, very important. What do order effect mean? For example, in the example that we said that we give مثلا in the beginning we give treatment B and then we wait for treatment B to finish and then we give treatment C, okay, to the same group of people. So how do I know that the effect of treatment B stopped before I gave them treatment C? Okay, so there might be some effects remaining from the treatment I gave them initially that will affect how treatment C works, and that's an order effect. And so that's or maybe مثلا because the same participant is participating twice, they may get fatigued, they may get مدري ايش, and all of those يعني, things that happen to them in the first test might affect what happens in the second test, and that's called order effect. And that's the main disadvantage of paired t-test. Makes sense. So we can reduce it by, first of all, counterbalancing. مثلا if they get fatigued, we or if they get a certain side effect, for example, we stop that side effect with the medication. We wait for that side effect to finish, and then we give them the new treatment we're trying to test. Okay, so we're counterbalancing, or we randomize the treatment. So, for example, we give some of them treatment B first, and then some of them treatment C first. Okay, and then so that will maybe reduce the order effect rate, because if treatment B for sure has an order effect, it won't be for all the patients because I didn't start with treatment B for all the patients. Okay, so theoretically that reduces order effect. Or we can delay the time between the treatment. So I can give treatment A now, and then I can give treatment C after a year. Okay, because I don't want any order effects. Everything here makes sense. Or I can avoid using matched pairs, or I can completely avoid it by using matched pairs or independent samples. And this is the only difference between matched pairs and paired, okay? Because matched pairs do not have order effects because we're using two different people. They're similar people, but they're two different people. Or independent samples. Obviously, we're completely eliminating order effects. Also, there might be bias from the participants in the paired HADA, and dropping out of one participant hurts. Okay, dropping out of one participant hurts because one participant dropping out means two dropping out. Obviously, this is also not the case in matched pairs, but it is the case in matched pairs actually, because if I have a sample size of 12, it needs to be in both group A and B. If one from here goes, I need to remove the pair I chose in group B. Okay, so dropping out of one participant really affects the study, unlike independent. So independent, every disadvantage here is an advantage here, basically. But we have a special HADA, which is the variability, okay, which is the advantage of the pair. And no, there's variance between the two different groups, and they may be very different from each other, which will affect the accuracy of the t-test. Okay, as we said, it will decrease the power. And that's why we use a special test called Wilks test. And Wilks test is a part of Jamovi. It's a special test that accounts for the variability. Okay, so it corrects the variability. You don't need to understand anything about this except that to correct the variability between the two groups, we use something called the Wilks t-test, which is it assumes that there is variability, and when calculating the difference, it puts the variability into account. Okay, that's the only thing you need to know. Okay, but it's still a disadvantage of independent t-test. No, there's going to be variability between the two HADA, and the variability invites confounding bias, and confounding bias might affect the results. So that's it for this lecture. Let's move on to ANOVA. I hope I'm not going too fast. If you have any questions about anything I said, I know I said a lot, please text me على طول, because usually you have very simple questions, but it will cause you a lot of confusion. So asking will make it a lot easier for you. Okay. So ANOVA. What is ANOVA? ANOVA just stands for analysis of variance. ANOVA is just فعاليات, fancy way of saying it. Okay. So it analysis of variance. We're analyzing the variance. Okay. So it is also a technique used to test differences between the means. So this is a continuation of last lecture, actually. Last lecture, we were comparing the two means, okay, A and B. Okay, we cannot compare more than A and B. ANOVA, the point of ANOVA is, what if, for example, we have C, and we want to compare all three groups together? طيب? In that case, we cannot use t-test. T-test only compares two. We have to use something called ANOVA, okay, which does the It tests for the difference of means between three or more different groups. Okay, when we have three or more different samples, and we want to compare all of them together, we use ANOVA. Okay, that's basically the idea. Okay, so how does it compare the HADA, the variance or the difference in means? It compares the variability within and between the means. Okay, so let's take an example just to make life a bit easier. We have group A, for example, and their values are 1, 2, 3, 4. We have group B, and their values are 3, 5, 7, 8, 9. Right? We have group C, and their values are let's say 2, 4, 6, 8. Okay, so these are three different samples, three different groups, and so there's variability within the group. Okay, so within the group itself, there's a variability. Okay, so this is the variability within the group. You remember how we used to calculate variability of a set? This is exactly the same. Okay, so the variability within the group, but then there's variability between the groups, the variability between A and B, group A and group B, the variability between group B and group C, the variability between group A and group C, the variability between group, I don't know what other combinations there. Okay, whatever. Okay, so this is variability between the groups. So it compares both the variability within the groups and the variability across the groups or between the groups, and it takes them into consideration. Okay, so what's the basic idea? If the variability within the group is done by individual differences between the participants, or errors of measurement between people in the same group. Okay, so I made the variability, مثلا, this one, the mean of this participant being 1, and the mean of this participant being 2, and this participant being 3, might be because there's actual differences between these 3 participants. It might be because I made an error while calculating. Okay, and between the groups, okay, so let's say I gave this group placebo, I gave this group treatment B, and I gave this group treatment C. Okay, treatment C. Okay, and the variability between the groups might be because there's individual differences. There's a difference between this person and this person. Maybe it's because an error of calculation again, or maybe it's drug B that's doing this difference. Maybe it's drug C that's doing this difference between here and here. Okay, so there's an additional cause of difference in the between the group variance, which is the treatment. Okay, and treatment's effect. So this is the difference between the variability within the group and the variability between the group. There's an additional effect, which is the treatment effect. Okay, so if there's a treatment effect and there's a difference in the variability between the groups, if there's a difference in variability between the groups, then there's probably a treatment effect. Okay, because probably the treatment is what's causing the difference between the 3 different samples. I know the 3 samples, I picked them randomly, and I picked them from the same population, so they shouldn't have a difference. But if there is a difference between the groups, then probably the treatment is what caused this difference. However, if there is no treatment effect, if treatment B is not doing anything and treatment C is not doing anything, then the variability between the groups is going to be the same as the variability within the group, because within the group is individual error and measurement, errors of measurement. Between the group is individual difference, error of measurement. If we remove this, they're going to be the same. Okay, because we're picking a random sample, 3 random samples from the same population. So they shouldn't have different variances. They should have the same variance, because we're picking from the same population. However, because we gave some treatment, we expect the variances between the groups to be different now because we changed something. If there is no difference between, if the treatment is not doing anything, then the variability between the group is going to be the same as the variability within the group, because basically now it's one big group. And no, the treatment didn't do anything. Okay, and this is the basic idea of ANOVA. And I compared these variabilities, and I found, for example, that within the group is equal to between the group. That tells me that the treatment isn't doing anything. the treatment is not statistically significant, وفروه. Okay, so this is how we use ANOVA. This is the basic idea. Obviously, there are calculations that come into play. Okay, so the main ANOVA we use is called one-way ANOVA. You don't need to worry about any other ANOVA. So it tests the variability within the group and the variability between the group. Okay, now the variability within the groups does not have to do with the null hypothesis. طيب? This is the null hypothesis. It's independent of the null hypothesis. So we cannot use the same P as we used earlier, which is result slash null hypothesis, or H0, let's say, being true. Okay, being true. We cannot apply this to within the group variability because the people within the same group, we didn't do anything to them. We're not hypothesizing anything for within the group. Right? We're comparing different groups. We're not comparing individuals within the group. Okay, within the same group. So group A for me is the same entity. Group B for me is the same entity. We're comparing group A with group B with group C. Okay, so within the group, we're not we don't care about the null hypothesis. But between the groups, this is dependent. Now we do care about the null hypothesis. Is there a true difference between the groups or not? Okay, and so that's why it's dependent on H0 being 2. This is exactly the same as the p-value we spoke about earlier, and this is important. It always comes. The difference between the variability between and within is that within we don't care about the null hypothesis, independent. In between we do. Okay, and it's dependent on H0 being 2. So if the two variables are similar, variabilities are similar, then we accept the null hypothesis because now the null hypothesis isn't, the treatment isn't doing anything. So we say, well, the treatment is not significant. Okay, this is what I was explaining earlier. If the variance between the group is significantly larger than the variance within, then we reject the null hypothesis. We say, oh, these treatments are doing something. Okay, so equations, and memorize these very, very well. Okay. Now, why I wrote memorize well here, other than the other slides, doesn't mean the slide is more important than everything I've been saying. It just means that in this slide, you probably won't understand. So just memorize it, okay? So in order to interpret the result of ANOVA, we need a ratio we call the F value. So what is the F value? It's a ratio. This is a question in the exam. F value, is it a ratio? Is it an interval? Is it a percentage? It's a ratio. Okay? So ratio is the same as percentage, صح? It's a ratio. Okay, so it's the ratio between the group, between the group variance and within the group variance. Okay, so this is the ratio. If the between the group variance is much higher than the within the group variance, then we reject H0. Okay, and so if we have a high F, we reject 0. We reject H0. If you have a low F, it means that there's no difference between these two, and so we accept H0. I hope you guys are comfortable by now, but wallah, what's H0, what's H1, and so on. So this is what I said. If F value is 1 or very close to 1, so for example 0.9, let's say, okay, this means that we accept the null hypothesis because this means that the between the group variance is equal to within the group variance. And this is what we've been saying. The treatment has no effect, so the between the group is the same as within the group. However, if F value is more than 1, we reject H0, and it's usually way higher than 1. It's usually 5, 5, 4 in these ranges. Okay, so if it's higher than 1, then we reject H0, and we say that this means that the between the group variance is more than the within the group variance, meaning that the treatment has an effect. Okay, the effect size in ANOVA is calculated using this, whatever the symbol is called, and they might ask you this. They might ask you the effect. You remember the effect size, how we calculated the confidence interval? The difference between the means over the standard deviation. That this is different. In ANOVA, we don't use that equation. We use this equation. This is represents effect size. Okay, so they might ask you in the exam, effect size in ANOVA is calculated using which of the following, and they'll give you this sign of the option. So this is the answer, and it is between the group sums of the square over the total sums of square. دي أبصموها يعني don't even try to understand it. خلاص, just memorize it like this. This came in the past. And what's the equation of effect size in ANOVA? It's between the groups sums of squares over total sums of squares. Don't just get a general idea, memorize it word for word. لأنه the other options are usually similar, between the group sums over within the group sums, and that's wrong. The answer is total sums, right? So that's it. So now comparisons. So what do we mean by comparisons? If we get, let's say, a higher value of higher than 1F, right? That means that the treatment is doing something. But which treatment is doing something? Is it treatment B or treatment C? Like, if both are doing something, is treatment B different from treatment C? Right? So F value only tells us that there's a difference somewhere. And there's a difference somewhere in wallah, C might be different than A might be different than B, whatever. There's a difference somewhere. Okay, so for example, let's say if A and C are exactly the same, but A is different from B, and also C is different from B. Okay, so C is not doing anything, but B is the one doing something. The F value will be more than طيب, but does that tell us in wallah B is doing something and C is doing something? لا, we need to do further tests to see which drug exactly is doing something and which groups are different from the others. Okay, and that's why we use something called comparison. Wallah, we start comparing the groups, A with B alone, and then A with C alone, and then C with B alone. Okay, so and we have different combinations, okay, which is called pairwise comparisons. Okay, so if we have three groups, we have three pairwise comparisons, which is مثلا A times B. We compare A with B, we compare A with C, and then we compare B with C. Right? So those are the only possibilities we can have. If we have four groups, we can multiply A by B, A by C, A by B, A by B, A by C, A by C, and then A by D, and then B by C, and then B by D, right? 1, 2, 3, 4, 5. There's one missing. C times D. Okay, so these are 6 possibilities. And then 5, 10, 6, 15. The same way, okay? And memorize, I would say, until 6. طيب? If they ask you more than 6, صراحة, that's even. They might ask you how many possible pairwise comparisons for ANOVA is there if we have 3 groups or 4 groups or 5 groups. So you need to memorize these well. بس صراحة حرام يسألوكم more than 6. أحس يعني. I don't know. زود. If you have energy, memorize them all صراحة, just to be on the safe side. So I wouldn't. If I was you, I'd memorize until 6. Like we have 2 types of comparisons. Okay, so these are the pairwise comparisons. So how do we compare? We have different tests. Okay, so we have priori tests, and from the word priori, prior means planned before the data is collected. So let's say I have A, B, and C. Right? Treatment B, treatment C, and this is placebo. A is placebo. Before we collect the data, we say that after we finish, we are planning this test to compare between group A and B, for example. Okay, so this is a priority test. Before we collected the data, we're comparing. We said we were planning to compare these two. Okay, so this is called a priority test. A post hoc test is chosen after the data is collected. So before the data is collected, I have no idea which test I want to do. After the data is collected, then I say, okay, let me do a post hoc test for A and B or A and C. Okay, depending on how the data looks. Right? So that's the difference between priori and post hoc. Priori is planned before, post hoc is chosen after. Okay. So priori is usually done when you already have a hypothesis in mind. And you're saying B might have a treatment but not C. And so I plan a test before to compare A and B. Post hoc is done after to make new hypotheses. Okay, now that I see that there's a difference between the groups, whether it was A and B or A and C or B and C, I don't know. So let me make new hypotheses. Oh, well, there's a difference between A and B, or there's a difference between A and C. So I start doing post hoc tests in order to see if there's that. Okay, so you don't need to know the part I said in the end. Just know the definitions. That's more than enough. Okay. Now, post hoc and priori tests. What are they called? This is the most important thing in the whole lecture. Okay. There are 3 types of post hoc tests. Actually 4. There's four types of post hoc tests. The first one is called Fisher's LSD test, okay? And this can be used both as priori and post hoc. Okay, so it's both priori and post hoc. And it can be used by any number of priori comparisons. So let's say I want to compare the test, I mean, the test we're doing is for 4 groups or 5 groups. I can do the Fisher LSD if I choose to do it priori. If I choose to do it post hoc, I can only do it across 3 groups. 4 groups I can't, 5 groups I can't. لازم exactly 3 groups. حتى 2 groups I can't. Okay, لازم exactly 3 groups. Okay, to use Fisher LSD post hoc. But if it was priori, I can use it for as many groups as I want. Okay, very important. And they have to be statistically significant. So, for example, if I get 3 groups and F value of 1, can I use Fisher LSD post hoc? لا. طيب. So, please, guys, very, very important to keep mind of all of these points. لأنه in the exam, they're going to bring you a case. I know full case. I did ANOVA for 3 groups who were taking treatment, blah blah. The F value was found to be 1, for example. Can I use Fisher LSD post hoc? لا, I cannot use Fisher LSD post hoc لأنه it's not statistically significant. However, if I have 3 groups, okay, and then the F value is 5.4, then I can use Fisher LSD, okay? And it is the most powerful test. It's called the liberal test. It's the most powerful post hoc test. And so what I'm saying is, if we have, this is definitely a question in the exam. If they bring you ANOVA with 3 groups, comparing 3 groups that have an F value more than 1, على طول pick Fisher LSD without even reading the other options, because it's the most powerful and we always try to use it. Unless we can't. We always use it unless we can't. And we can't if this is more than 3, if we're comparing more than 3 groups, or if the F value is equal. Because these are the 2 cases in which we cannot use Fisher LSD post hoc. Not priori. This does not apply for priori. Obviously, in priori, we don't even know if the data is statistically significant or not, and we can use it for more than that. Another point, if they say, which of the following tests can we use priori, you pick Fisher LSD على طول. Why? Because when you see the rest, they can only be used post hoc. They can only use B post hoc, okay? So if they say, which of the following tests do I do priori? Fisher LSD على طول. So Fisher LSD is the best test in this slide صراحة. And it's probably going to be the one asked about. If they don't ask about more than one, probably going to be Fisher LSD, okay? The second test is called Tucky. Tucky is HSD. And this is only post hoc. You cannot use it priori. It's used when there are more than 3 treatments. It's the second best thing. After Fisher LSD, if I can't use Fisher LSD because I have more than 3, خلاص, I'll use Tucky. It's the second most powerful test, and it controls family-wise error rate. So the description of Tucky is, it compares more than 3 treatments or groups while controlling type 1 error or family-wise error, okay? Controlling type 1 error. You don't need to understand this, just memorize it, okay? This is exactly how it's going to be asked. طيب? They're going to say, well, what is Tucky? And it's basically a test that compares more than 3 groups while controlling type 1 error. And let's review what's type 1 error. Type 1 error is rejecting the null hypothesis when it's true. Okay? So basically a false positive. James-Howell test, very low yield صراحة. It's exactly the same as Tucky, but it does not assume equal variances. Honestly, I don't know what that means. Very low yield. I put it for completion's sake. If they ask you, what's the difference between Tucky and James-Howell, Tucky, James-Howell does not assume equal variances. Tucky assumes equal variances. Okay. And then there's Bonferroni test, and the main thing you need to know about this is the definition. It is a general post hoc procedure. General is an important word. It's a general post hoc procedure that divides the significance level by the number of the statistical tests done. Okay, so this is the Bonferroni test. If we did 5 tests, for example, and our significance level, the alpha we chose is 5%, let's say. So we divide 0.05 by 5, and that's the Bonferroni test. صراحة, the calculation is not important. The equation is important. This sentence is very important. In the Bonferroni, they might ask you which test divides the significance level by the number of statistical tests done. That's Bonferroni. Which test is the general post hoc procedure? That's Bonferroni. Okay. Very high yield slide, صراحة. They might get you more than 3-4 questions on this. Finally, the last lecture, which is Principles of Biostatistics. Disclaimer, no disclaimer, warning, ما أدري. المهم إنه this slide, these slides I used were our slides, and a new doctor came to you guys. Her name is Dr. Noura. I don't know if she uses different slides than our doctor. I don't know if she'll teach different stuff. However, the objectives are the same, so the content should be the same. Like I don't think she's gonna add new content, but you need to go over your slides. Then the time I'm recording this, you haven't taken a lecture from her yet, أصلاً. So we weren't able to obtain her slides. So I prepared it from our slides, but inshallah, the content is the same. I tried to cover everything Dr. Hala covered, which is our doctor, even if I didn't think it was important, because maybe Dr. Noura thinks it's important. So I tried to cover everything, but go over her slide, Dr. Noura's slides anyway. And if you have any question, you can always ask me. Okay, so now another thing is that this lecture, صراحة, it's very important for you as a doctor in general, and for anyone who's interested slightly in research. حتى if you're not interested in research, these 3 lectures are very important. And you'll use it in your everyday life تقريبا as a doctor. So it's good if you understand it, not only for the exam. Okay, so an overview. The father of epidemiology is called John Snow, and he demonstrated that the risk of cholera was related to drinking water in UK. So this is epidemiology. If you remember, there's many overlapping things with the epidemiology lecture introduction Dr. Hassan gave. So I didn't repeat anything. If it may have been repeated in the lecture, but I didn't repeat it if I already mentioned it in the epidemiology section in the first lecture. So make sure you read that as well. I know it overlaps with this. Okay, so epidemiology is the distribution and determinants of diseases. Okay, so distribution, where are they distributed, among who, and determinants are risk factors. Okay, so he demonstrated that the risk of cholera was related to drink water. So he demonstrated a determinant of a disease, and that was when epidemiology was first introduced. Okay, and so new definitions. Obviously, you all need to know all definitions of epidemiology or different types of variables. Okay, so dependent variables are called outcomes. Okay, independent variables are called exposures or risk factors. So dependent variables depend on the independent variables. So basically the independent variables are what give us the dependent variables. So for example, smoking is a independent variable. Lung cancer is a dependent variable, lung cancer, okay? And you need to know this very well, and the way Dr. Hala used to ask is she used to bring a case and she used to tell you, is this a dependent or an independent variable? What type of variable is smoking, for example? So you need to really understand it. So whatever causes something, okay, is independent, the risk factor, okay? And what this risk factor causes is the outcome, okay, which is the dependent, okay? So now morbidity is disease, mortality is death. Modes of expression, we can either use absolute numbers, we can use rates, we can use ratios. That's pretty much it. طيب, study designs, very, very important, guys, okay? Study designs, we have 2 main different types, which is experimental studies and observational studies. From the name, experimental studies are where we experiment, we do something, okay? We do something to the patients, okay? So this is experimental, we do something, okay? And for observational, from the name, we just observe, we just watch, okay? We don't change anything for the patient. مثلا, for experimental study, the only example is the randomized control trial, when I give patient treatments, okay? So that's an experimental study. Observational, I just watch. For example, I want to see, well, is smoking associated with lung cancer? So I just watch Minbari. I take people who smoke and people who don't smoke, and I see if people who don't smoke have more lung cancer than people who smoke or whatever. So that's observation, okay? And there are many different types of observational studies. So we said the only experimental type of study is randomized controlled trials. We're going to talk each of these in very much detail. This is just an overview. Okay, so observational studies, again, are classified into two types: analytic studies and descriptive studies. Descriptive studies describe the population at one point of time. Describe population at one point of time. Okay, so and the example of this is cross-section study. So which of the following is a descriptive study? Cross-section. Okay, so this I can see it coming as an MCQ. So what do I mean by describe the population? So what is a cross-section? When you go to someone, you distribute a survey, and in the survey you ask, are you exposed to, are you a smoker? Yes. Do you have lung cancer? Yes. Okay. So you're describing the population. Well, this is a smoker that has a lung cancer. But in analytic studies, you're not describing a population. You're trying to see if something causes another thing. Okay. And that's when, for example, it can be prospective or retrospective. For example, you see many people have lung cancer, and then you go back and see if those people are smoking, and then you try to analyze this relationship. So this is analytic. Okay, it's not a descriptive study. Okay, so let's talk about each of these in detail. So the first type is cross-sectional, and this is what we all do here in the university: surveys and this is the best way to start research, and it's the easiest and the cheapest. Okay, so in this case, exposure and outcome are assessed simultaneously among individuals in a defined population at one point of time. Very, very important. Also, if you read the titles of cross-sectional, you always see prevalence of blah, blah, blah in Al Faisal Medical Student. So we specify the population, and we're looking at the prevalence at this specific point of time. Now, today, in this period of time, I want to see the prevalence, for example. Okay, so we're assessing at one point of time. These are very important, and these are the differentiating factors between the types of studies. Okay, so the definition is important. So exposure and outcome are assessed simultaneously. So in the same time, I'm asking you, do you have the exposure? Yes. Do you have the outcome? Yes. In the same time. Mo wallah, you have the exposure now, and then I look later on if you had the outcome, or I go back to your medical records to see if you had the exposure. Okay, so you understand what what I'm getting at. Okay, so exposure and outcome are assessed simultaneously. This is the key word. At one point of time, this is another keyword. Okay, so we measure this by prevalence, as we said, prevalence rate. Okay, so we have this box that's going to be very important. Basically, this is the outcome, the exposure. Are you exposed? Yes. Do you have the outcome? Yes. This is A. Are you exposed? Yes. Do you have the outcome? No. This is B. Are you exposed? No. Do you have the outcome? Yes. This is C, and so on. Okay. So we use this table to calculate a lot of stuff. Okay. So for cross-sectional studies, we use something called prevalence rate. Okay. So prevalence rate outcome in exposed. So exposed and has the outcome. So you measure A over the total percentage of exposed people. Okay, so A plus B. Okay, so you want to see how many people that are exposed are actually have the outcome. So this is the prevalence rate outcome in exposed patient. The prevalence rate outcome in non-exposed is C. So someone that has the outcome but is not exposed. Okay, so C over the total, C plus D. Okay, simple enough. So let's get an example. So now we get something called the prevalence ratio or rate ratio, which is PRR. Okay, which is basically this over this. So the prevalence rate outcome in exposed, which is written as like this, PE over PE no and PE no 0. Okay, so then we divide this by this. Okay, so what does that tell us? We'll explain in a bit. So let's take an example. This example, the relationship between smoking, which is the exposure, and weight control measures, or people who go to control their weight, whether exercise, gym, surgeries, whatever. Okay, so what is the relationship between these two variables? So people who smoke and did the weight control measures are 420. So the PE will now equal to 420 over the total people who smoke, which is 1157. Okay, so that will give us 0.36. And then we get the P non-exposed, which is 176. So they're not exposed, but they did do weight control measures. That's 176, and their ratio over the total is 176 over 818, which is 0.22. Okay, so then we divide 0.36 over 0.22. So what does this tell us? It gives us 1.64. What does this tell us? This tells us that people who are exposed to smoking are 1.64 times more likely to be involved in weight control measures. Okay, so this is why we do the ratio. Okay, to give us how much more likely. 10%. Okay, so this tells us how much. I don't know if I'm gonna be able to finish Salah with 10%. I'll see if it reaches 5%. I might be pausing or coming back. Okay, so where was I? Oh, and it tells us how much more is the exposure probably gonna lead to the outcome. Okay, so 1.64 times. Okay, and advantages of cross-section studies are that they short duration and low cost. That's why all medical students start with it. Disadvantages is reverse causality. Okay, so because we're assessing the exposure and the outcome in the same time, we don't know what comes first. Okay, but if we're not doing exposure and outcome at the same time, we know exactly what came first. We know if wallah he was exposed or the outcome came first. Okay, so we cannot establish causality. We cannot say that one led to the other. What came first, outcome or exposure? That people who would go to weight control, that leads to smoking. Maybe not. It's not the other way around. Okay, so reverse causality is the biggest disadvantage of cross section studies. Okay. Now cohort studies. Cohort studies are when we start with the exposure, then we follow up to check the outcome. Okay. So this is the main difference between cohort and case control, which is the one we're gonna explain later. Okay, so cohort is, for example, we want to determine the association between smoking while pregnant and low birth weight babies. Okay, so the exposure here is smoking while pregnant, and the outcome is getting a low birth weight baby. Okay, low birth weight baby. Okay, so this is the exposure and this is the outcome. So we start with the exposure. We get a group of people, pregnant ladies who smoke, and then we see how many of those got a low birth weight baby. Okay, and the example, and then we also get a control group, obviously, which are people who don't smoke, and then the calculation is exactly the same as this. Okay, we get but this time it's called relative risk instead of PRR. Okay, we call it relative risk. Okay, and so if relative risk is more than 1, if we take the ratio and we get a relative risk more than 1, that's positive association. And here we can say that this exposure caused the outcome because we know that the exposure came first. And that one, we asked at the same time, wallah, did you? But in this case, we see if the exposure came first, we know for a fact, so we know the exposure caused the outcome. Okay, it cannot be the other way around. Okay, so in this case, if the relative risk is more than 1, we say that the exposure caused the outcome. If the relative risk is exactly equal to 1, then exposed and non-exposed are the same aslan, and so we say there's no relative risk, there's no association aslan. If RR is negative than 1, then we say there's a negative association. So people who smoke or pregnant ladies who smoke actually have better babies. So it's protective. Smoking is protective. Okay. So in this case, in our example, let's say the relative risk is 2.4. So that's a positive association. So smoking pregnant ladies are 2.4 times more likely or have a higher relative risk compared to people who don't smoke to get a low birth weight baby. Okay. So now we're still talking about cohort studies. We don't interpret relative risk as the relative risk. They usually don't give you they do give you the relative risks, but we don't interpret it, we don't write it as a relative risk. We write it as increased risk. Okay, what is an increased risk? The equation for increased risk is relative risk minus 1 times 100. So for example, in that case, we got the relative risk as 2.4. The increased risk is 2.4 minus 1, which is 1.4 times 100, which is 140. So we read it as there's a 140% increased risk of getting a specific outcome after a specific exposure, okay? So in our example, the specific outcome is low weight and low weight birth, whatever. And specific is the specific exposure is smoking, okay? Now, let's say, for example, we have a negative association, okay? And the relative risk turned out to be 0.2. Then we put it in the equation, 0.2 minus 1 is negative 0.8, times 100 is negative 8. So now we say that there's an 80% decreased risk, not increased, decreased, because we have a negative value, risk of getting the specific outcome after being exposed to a specific exposure. For example, let's say, what is the chance of getting breast cancer for females if they were breastfed, okay? So people who were breastfed actually got less breast cancer. This is a negative association. So breastfeeding is protective for breast cancer. And so there's a decreased risk with this specific exposure to get the specific outcome, okay? Hope that makes sense. So there are two types of cohort studies. We have prospective and we have retrospectives. From the names, pro means in the future or after. So we assess the exposure at present time. Right now, I go to the hospital, I collect a couple of pregnant ladies, some who smoke, some who don't smoke. Okay, and then in the future, I see in Wallah when they give birth, I see if their babies were low weight or normal. Okay, so this is prospective. Retrospective is I assess the exposure in the past. So those had smoking pregnant ladies. Okay, after they gave birth, I come, I see, Wallah, okay. So again, okay. So in retrospective, I come right now and the outcome already happened. So they already gave birth, okay? And I see how much of them were smoking in the past, okay? So I go back to the past and see how many of them were smoking and then see in Wallah low molecular weight, low weight babies, and then I compare. So it's exactly the same, but in perspective, I assess the exposure at present time. So it's a present to future study. In retrospective, it's a past. I start from the past and then come to the present, okay? So it's a past to present study. So I go back and see who is smoking, and then I come now and see, wallah, yallah, who gave a low weight baby and who delivered a normal baby, okay? So the advantages of cohort studies is that they are direct measurements of incidence. There is no way there will be reverse causality, okay? Very, very strong advantage for cohort studies over cross-section. Generally speaking, cross-sectional توفيرين. Cross-sectional يعني they're not preferred. They're very weak studies يعني بريالين. Okay, so people usually use randomized controlled trials, cohort, these stuff. Okay, another advantage is that they're suitable for rare exposure because we're starting from the exposure. We can hand pick the exposures. So we go, wallah, if you want rare exposures, if you want to test rare exposures, we can handpick them. So this study is suitable, it's study design. And we'll compare it to case controls and we'll see why case controls are not suitable for rare exposures or not none of the other studies for that matter, okay? And then it's possible to examine a wide range of outcomes, okay? So I took this exposure and then I don't only have to test the outcome I'm looking for, okay? I can see, wallah, all the outcomes that happened and then maybe my study is about this specific outcome, but maybe I can then do another study with the same set of data for another outcome, okay? So this is also another advantage for a cohort. One thing I want to note is that it's suitable for rare exposures, but not suitable for outcomes, for rare outcomes. So because I can't pick, for example, let's say, well, I'm looking for a very rare outcome, a very rare disease, okay? And I take 100 people with a certain exposure. And I want to see if this exposure leads to that outcome. If I take this 100 people with this exposure and I do, and none of them have this rare outcome, does that mean in all this exposure is not associated with the outcome? Doesn't mean this, because I didn't get this outcome because it's rare. Maybe it's not associated, but maybe it's rare. That's why I didn't get it. So it's not suitable for rare outcomes, but it's very suitable for rare exposure. Okay. Case controls, nice way to memorize the difference between case controls and cohorts. Case control, we start with the outcome. Okay, so it starts with case. So we start with the case. We start with a case of systemic lupus. Okay, so we start with the outcome. Then we go backward and check for exposure. Then okay, so let's say I get people with lung cancer. Then I go back and then I see, wallah, were you guys smokers? Okay, so this is the difference between case controls and exposures. And in this case, we don't use the same calculation as the relative risk and PRR. Instead, we use odd ratio. Okay, and what is odds ratio? Odds ratio is the percentage. Is basically A times D. So people who have the outcome, obviously, and were exposed over the people who did not have the outcome. We pick those, obviously. We pick the people who don't have outcomes. They're called controls, and we're not exposed. Okay. We multiply them and we divide by this crossing. Okay, and this gives us the odds ratio. Okay, the interpretation of the odds ratio is exactly the same, but the calculation is not the same. So important to know the difference. Okay, so in this case, for example, to get the odds ratio, we multiply 66 by 134 and then the other 66 by 22. Okay, so we're assessing the association between artificial sweetener and bladder cancer. So we took patients who have bladder cancer. We chose patients who do not have bladder cancer. So these patients do not have, these patients do. And then we saw which ones took, which ones took artificial sweetener, which one didn't. And then we got the odds ratio. So this table can be given to you and they tell you this is a cohort study, and then you need to do a different calculation. If they tell you this is a case control, you need to get odds ratio. If you need to do a cohort, you do relative risk, okay? So very important to differentiate between the two. So an odds ratio, if the odds ratio is more than 1, okay, the exposure is associated with increased risk of developing the outcome, okay? Again, this is the same exact interpretation. The only difference between case controls and HADA, in case controls, we start with the outcome. In cohorts, we start with the exposure, okay? If the odds ratio is less than 1, the exposure is associated with reduced risk. If OR odds ratio is equal to 1, there's no association. So how do we select these controls? Okay, how do we select them? Controls are people who are known to not be exposed to the exposure under study. This is very, very important. Right? So for example, if we have, if we want to test the lung cancer and smoking, okay? The control group, should I get people who have myocardial infarction as a control group, ولا people, injured patients in general, اللي ما لهم دخل stuff that are caused by smoking, for example, patients that got trauma, for example, okay? Which one is a better control group? Definitely the injured patients. We cannot use myocardial infarction as a control group. Why? Because myocardial infarction is related to smoking. Smoking can also lead to myocardial infarction. I can only test one outcome at a time, right? So I want lung cancer. The control group should not be associated with smoking at all. Okay, it should be something that's completely not associated. We know that this is not associated with smoking. If there's an association with the exposure, we cancel that control group. That's not a good control group, okay? So controls are people who are known not to be exposed to exposure under study, okay? So the advantages of cohorts over, or case controls over over cohorts are that they're short and cheap. Cohorts are usually long and expensive. Case controls are practical for rare diseases, okay? So this is exactly the same concept I was explaining, but this time it's the opposite. It's practical for rare outcomes. You know, I can hand pick the outcomes, but obviously it's not suitable for rare exposure, because again, if we get 100 people with the outcome and none of them have the exposure, that doesn't mean the exposure doesn't lead to the outcome. It just means this exposure is rare, okay? So it's not good for rare exposures. And the advantage is good is that it can test for many hypotheses, okay? So after we establish an association, we can then do multiple tests, multiple hypotheses can be made, okay? Disadvantages is recall bias, okay? Because Now we're getting a patient who had, for example, let's take away the example of lung cancer. There's something else, and well, a certain disease, and you ask them, did you have this exposure? They may have had this exposure 10 years ago, so they did have the exposure, but they tell you no, then they forgot. Okay, so it's there's potential recall bias in HADA. Okay, and another disadvantage is indirect estimate of relative risk. Okay, so if the odds ratio, for example, is 6.37, طيب, that's not very accurate. No, that's not relative risk. Okay, it's not the same as a relative risk. Although we're interpreting it as a relative risk, okay, we're saying this is the same interpretation as a relative risk, but it's not directly a relative risk. Okay, we didn't calculate it the same way as a relative risk, so obviously it's less accurate. Yeah, so that's all you need to know. The most important thing is the rare diseases and rare type thing. Okay, now last. مطولين. لا, I'll go get my charger and come back. I don't know if there's an option to pause the recording. Yeah, there's an option to pause the recording, so I'll pause and come back. Okay, I'm back. Wait, I think we stopped. Yeah, we're just gonna start randomized controlled trials. So as we said, randomized controlled trials are the only type of experimental study, okay, in which we actually do something to the patients. So we assign exposure. We assign the exposure. So for example, exposure might be the treatment, the new treatment we're trying out, okay? And then follow up and see if a certain outcome occurs. So it's always prospective. The exposure has to be assigned random. This is very important from the name, randomized controlled trial. Has to be randomly assigned. If it's not randomly assigned, if there was any bias anywhere in distributing this exposure, then the randomized controlled trial becomes weaker and weaker. Okay, so and we use the same formula as cohort study because this is basically a cohort study, but instead of instead of looking for a certain exposure and starting with it, we are doing the exposure, if that makes sense. Okay, so this is also we also use the relative risk. The control groups, so we have a control group and a treatment group. The control group receives a placebo. The placebo is basically, مثلا, if the drug is a yellow small pill, the placebo is a yellow small pill, but it is not actually active. Okay, it's just something, but it has to be indistinguishable physical features from the actual medicine. So it has to be the exact same size, the exact same color, the exact same taste. Okay, and so something that's not distinguishable from the other. عشان maybe a participant from the placebo group will go ask someone from the treatment group will tell them, I took a red pill. And if the placebo is yellow, then the placebo will know they took the placebo and treatment will know they took the treatment. Okay, so we don't need anyone to know what they took. We don't want, even me as the researcher, I don't want to know what I gave this person. Okay, to eliminate all bias, and then we interpret the results. Okay, so to do a randomized control trial, we need some criteria. The first thing is safety. We need to exclude anyone that may be harmed from this trial. So, for example, if I have a drug that may be contraindicated in pregnancy or teratogenic, definitely I have to exclude all the pregnant. Okay, and so on. And also, I have to select individuals that will likely comply with the randomized control trials. People quitting in the middle is going to hurt. Okay, and that's it's called attrition bias, in which people quit in the middle of the study. So that weakens the study. Okay, so randomization. Each subject has to have the exact same probability of receiving a given treatment. Okay, so when is this flipped? When I like a patient more than a patient and I choose to give that patient not the placebo, the treatment. Okay, so although they were originally assigned the placebo. Okay, so that's bias and that weakens the study, and that's not random. Okay, so this is done to reduce confounding bias. It can be done by alphabetic rule or by computer, the randomization, and should preferably be double blinded. Okay, so it can be sometimes single blinded. No, only the patient doesn't know. As a researcher, I know who's getting the placebo and who's getting the treatment, but the patient doesn't know, and that's a weak study. طيب, a weaker study. It's preferable to be double blind. RCTs are the best study design ever. Okay, it's the best type of study design because they have the lowest potential of confounding bias if done properly, sample selection bias, and information bias. So our HADA, it doesn't depend on, for example, asking patients, oh, what happened, or were you exposed, or whatever. Okay, so this is open for bias. Other studies all have risk of confounding bias. They all have risk of sample selection bias. But RCTs, if done properly, تقريبا has no one of all of these biases, and that's why it's a very good study and study design. But obviously, it's very expensive. It's sometimes unethical. يعني. Are you using humans as lab rats? So some people say RCTs are unethical, and because your drug might kill someone, you don't know what the drug is doing. That's why you're testing it, صح? So you're only hypothesizing that the drug is working. If I give it to someone and I kill them, although they consented, بس يعني برضه. So you're basically using humans as lab rats, and so that's why some people say it's unethical. It's very expensive. It takes a very long time, and it reduces generalizability, which means because of this criteria, which is the safety criteria, we exclude so many people from the study. So when we say this drug works for obesity, for example, does it work for everyone, or does it work only for the people we chose? Because we excluded many people. But does it work for example, if we took patients who are non-pregnant, for example, طيب, and we gave them a drug for hypertension that worked. Does this drug work for pregnant ladies? Well, we don't know. So the generalizability is very low. We cannot generalize with RCTs. طيب, validity. So what is the validity of the study? When conducting a study, we have three concerns, okay? And the three concerns are the sample, the target population, and the general population, okay? So basically, we take a sample, and we take a sample from a target population. For example, if we chose we want to do, let's say, pregnant ladies, okay? So pregnant ladies is the target population. The sample is a couple of those, so 100 of those. And then there's the population, which are non-pregnant ladies and males as well, and everyone outside this target population, okay? So there's internal validity and there's external validity. The internal validity is the extent to which the analytic correct for target population inference. Okay, so the extent to which analytic inference from the study sample is correct for the target population. So we have, as we said, three circles. Where do I do the circles here? Right? We have sample, we have target population, then we have the other population, the general population. So can I apply the results on the target population? This is called the internal validity. Can I apply the results to the general population? This is called external validity, okay? So how valid these results are for the target population is internal validity. To the external, to the general population is external validity, okay? So this slide is very important. I don't know why I'm not bolding and underlining, maybe because of the space. This is very important. It's always asked, okay? So this is analyzed. The internal validity is analyzed by the amount of potential bias. Again, there are three main types of bias that you need to know. Okay, the first one is called selection bias. So if you have more bias, obviously it's less valid. The inference is less valid. Okay, so we have selection bias, which is error due to difference between people selected for study and those who are not. So if I have a target population of pregnant ladies, for example, so and then I start selecting a specific group of pregnant ladies that do not represent even this target population, then that's a sample selection bias. And so the sample is not represented. And so if I want to remove this bias, I need to pick a representative sample, okay? The second type of bias is information bias, which is known as observation, misclassification, measurement biases, okay? And this is basically an error in the assessment of either exposure or the outcome. So I might take someone that I think has the exposure and they don't, بالغلط. And I might take someone who has, I might think someone had the outcome and they didn't. Maybe they told me they had the outcome and they didn't. They're lying. Maybe they forgot. Maybe you might have. This is all type of information bias. And so we have different types of information bias. We have misclassification and exposure. Okay, which are recall bias, for example. And while I asked the patient, were you exposed to this? They say no, and they were actually exposed to it, but they don't remember. Interviewer bias, in which I'm introducing leading questions. So, for example, the questions have to be open-ended, and the patient has to remember alone. If I ask the patient, were you exposed to smoking, for example, or were you exposed to a GI infection, and did your stomach hurt or madri ايش? They may say yes, just because you led them to saying yes. If you ask them, did you feel anything, the general question, then they'll probably say no. Okay, either they forgot or no, they didn't. But if you lead them to saying yes, then that's interviewer bias. Then there's also error in data entry. Okay, that's the obvious one. Then misclassification and outcome may come as diagnostic bias. You diagnose this as the outcome when it's a false diagnosis, or error in data entry. So this can be minimized by double blinding and standardizing detection protocols. So if the exposure is assessed by a certain measure by one person conducting the research, other people who are conducting the same research have to use the same measures, the same questions asked, the same type of communication, and so on. Okay, in order to not have different okay. And then we have confounding bias, which is I explained it earlier, a third variable affecting the relationship between exposure and outcome. Another risk factor to the disease that is associated with the exposure study. This is a confounding bias, okay? So to minimize the risk of confounding bias, we need to restrict to one category, okay? So we restrict, for example, if I don't want smoking, for example, as a confounding bias, I know smoking also affects my outcome, and I'm testing something else, and I don't want smoking. So I pick non-smoking people, okay? So I specify, I restrict, no, I don't want smoking people in the study. That eliminates that confounding bias. Another thing is matching participants and using RCTs, okay? Because if I match participants, I'm decreasing the variability, again, per test. I'm decreasing the variability between the two groups. And in that case, there's less probability of confounding bias. And then using of RCTs, we can use multivariate analysis techniques, okay? And analysis is obviously after the results are obtained, okay? So let's say I obtained the results and there was actually a confounding bias. The only bias that I can correct after it already happened is confounding bias. I have something called multivariate analysis techniques, which account for confounding biases. And so they correct them while analyzing. You don't need to know how. And these are either logistic or multiple linear regression. So regression is the main word, regression tests, in which or technique in which they eliminate the confounding bias after it already happened. So during analysis. So this is high yield, okay? And the only thing that can actually change after HADA is confounding bias. This is the only type of bias that can be adjusted at analysis level. External validity is another name for generalization, as we said earlier. Screening. But screening is very important. What is screening? Screening is used to detect diseases early on in order to reduce morbidity and mortality. Screening tests, okay? So, for example, for breast cancer, the screening test is mammography. So you come and check for breast cancer, even if the patient was, or the person was asymptomatic, okay? So the disease course is no disease, and then you get the disease, but in something called the subclinical phase. Subclinical phase is in which you have the disease, but it's asymptomatic. Asymptomatic. And then you have the disease again still, but symptomatic. Okay, so now it's the clinical phase. It's not the subclinical phase. So if you detect a disease over here, this is the main goal of screening, is detecting the disease in its subclinical phase. And no, the disease is there, but the patient doesn't know. And so we want to detect it early on in order to remove it early, even before the symptoms start, okay? And so the screening test should be simple, inexpensive, because we need to do it regularly, and asymptomatic, okay? For asymptomatic patients, okay? And If the patient presents with symptoms and then you start doing tests, those are not screening tests. So those are diagnostic tests. You're trying to make a diagnosis because you already see symptoms and you want to see what's the cause of symptoms. But screening test is something I do every year, for example, to test if I have disease in subclinical phase. And obviously, I don't do it for all diseases. I only do it for certain indicated diseases in which I have good screening tests. For example, breast cancer or colon cancer or whatever. Okay. The reliability of screening tests. So there are two measures for screening tests to be valid. There's the reliability and there's the validity. Okay, or to be good. Okay, so the more reliable the screening test, the better, obviously. And how do we test the reliability? The reliability is basically the reproducibility of the test. So if I do the same screening test for other patients, for example, if I do them for group A of patients and they turned out to be positive, for example, and then I did it for the same test for other groups of patients that I know have the disease, and this time it turns out to be negative. So this screening test is unreliable because sometimes it shows positive, sometimes it shows negatives for people who I know have the disease. Right? So this is bad. This is a bad screening test. So the reproducibility of the test is its reliability. We calculate it by percentage agreement. So, for example, we have these two pathologists, and we have three. Either the patient has melanoma, or they have intermediate, or they have benign. Okay, so we calculate the percent. For example, we have two different pathologists check the same 37 cases for melanoma. Okay, so these 10 patients, both pathologists agrees that they have melanoma. This patient, pathologist 2 said they have melanoma, but pathologist 1 said they have intermediate, not melanoma. And then benign as well. Pathologist 1 said it's benign, pathologist 2 says melanoma. So they didn't agree on these two, but they agreed on these 10. And that's the case for these three. So these three were the one agreed on. And so we add them together and we divide them by the total and we see how much percent they agreed. So they agreed for 70% of the cases. So we say the reliability of this screening test is 70%. Okay. Now the validity, which is more important than reliability, and this is something you'll use for everything. Hatta right now in third year, you see these words a lot. This is a highly sensitive test, but low specificity, or highly specific but low sensitive. And if you don't know what these means, you'll be lost. So this is what sensitive and specific mean. So a sensitivity is the probability of positive test if the disease is present. Okay, so let's say I get people who have the disease. How many of those will the test positive for? Okay, so that's how sensitive the test is. How specific the test is the probability of negative if the disease is not present. So I get a group of people who do not have the disease, definitely do not have the disease, and I see this test always show negative in those, or sometimes it shows positive. Right? And so this is the specificity of the test. Positive predictive value is the probability of a true positive. So it's basically the probability of testing positive and having the disease. Okay. And then negative predictive value is probability of true negative, which is the probability of getting a negative test in people who لا دقيقة again. Positive predictive value is the probability of getting a true positive طيب in people who the screening test was positive. I don't know if these people have the disease or not طيب, but if مثلا I get people who so the difference between sensitivity and positive predictive value is in sensitivity I start with people who have the disease and then I see how many of those will the test positive for. Okay, in positive predictive value I get people who tested positive and then I see how many of those were actual positives. Okay, so the equations we come to this table, which is a very good table. So these are the test results, positive, negative, and the disease status. Either have the disease or does not have the disease. Okay, so for sensitivity, we have we take A, طيب, and then we divide it by A plus C, by the total of A plus C, which is people who definitely have the disease. So how many people who have the disease tested positive? That's sensitivity. Okay, so A plus over A plus C. Specificity is how many people tested negative who did not have the disease. So D over D plus D. Okay. So in sensitivity and specificity, we go like this, downwards. In positive predictive value, we want to see how many people tested positive are actual positive. So A over A plus B this time. Then for negative predictive value, the same. D over C plus D. Okay, so we go horizontal. So for predictive values, we go horizontal. For sensitivity and specificity, we go down. Okay, so let's have an example here. We want to get sensitivity, specificity, everything. Okay, so we said 5,000 women underwent a test for blood glucose at 24 weeks of gestation. The following results were noted. Okay, so people who have gestational diabetes, here yes and no, and positive, negative test. Okay, so for sensitivity, we want to see how many people who have gestational diabetes, okay, so 190 total, how many of them tested positive? So that's 186, okay? So 186 over 190 times 100, that's a very high specificity, 97% of top or something like that. So I don't know if this is the correct answer, by the way, but no. Very high sensitivity. So we say this test is highly sensitive, okay? Yani, when this test is positive, then it probably means that this person has the disease. Specificity, whatever it's called, is people tested negative and they don't have gestational diabetes. So 4753 over 4810. Again, very high specificity. And so this means that if this test turned out to be negative, then this patient is very likely to actually not have the disease. So it's a very good test, both if it turned out positive or negative. Predictive value, you do positive predictive value, you do 186, which is people who were tested positive and have the disease, over the total amount of people who tested positive. So 243, which is, and again, it has a good positive predictive value and it has a good negative predictive value. So 4753 over 4757. Very good negative predictive value. Okay. So usually, and this test is very good. It has good everything, but usually the tests may have high sensitivity. So when it's positive, that means they probably have the disease. But when it's negative, does that mean they don't have the disease? I don't know, because the disease has low specificity. Okay, so that's usually the case with actual clinical tests. Some tests have good negative predictive value, but it's only used. For example, D-dimer test. It has a very good negative predictive value, which means if it's negative, then this patient definitely doesn't have the disease we're looking for. Okay, but if it's positive, it doesn't mean anything. It can mean 100 things. Okay, so this is why sensitivity and specificity are important, and the concepts of them are important. That was it. I hope I didn't go too fast. If you have any questions at all, let me know. As I said, it's too late now, but I advise, after finishing each lecture, go back to its past papers and then move on to the next lecture when you're memorizing, because that's better to retain information. I'd appreciate if you scan this QR code to give us feedback and let us know how to improve. And best of luck on your exams.